What if a galaxy could break the sound barrier of space itself? It's a wild thought. A concept that feels more at home in the realms of science fiction than astronomical fact. We tend to think of space as still, silent, and eternal, a cosmic vacuum where things drift slowly, like leaves on a vast, empty pond. But not everything out there moves gently. Some things rocket through space with unimaginable force. Some things leave chaos in their wake. And one of those things is real. A cosmic giant. A silent bullet through the darkness. But before we continue, subscribe to the channel so you don't miss out on any of these videos. This is the story of NGC 7619, a galaxy that doesn't just move, it plows. It races forward through the vast, hostile landscape of its galaxy cluster like a titan unbound, carving a path through plasma, gas, and dust, pushing the very limits of what motion can mean in a vacuum where there is no air, yet still a sound barrier. But how can something break the sound barrier in space? How can a galaxy be supersonic when sound can't travel in a vacuum? The answer lies in the hidden oceans of hot gas that fill galaxy clusters. In the same way that sound travels through air on Earth, waves and turbulence can travel through this intergalactic soup. This medium is not empty. It is hot, thin, and deadly. It exerts pressure. It pushes back. And in that arena, something incredible happens. A galaxy, ancient and vast, surges forward so fast that it causes shockwaves to ripple through this invisible plasma. This isn't science fiction. It's astronomy, and it's happening right now. NGC 7619 doesn't announce its presence with color or spirals or fireworks. It's an old elliptical galaxy. On the surface, it might seem dull to some. No vivid arms. No glowing blue nurseries. No spiraling dance of chaos and creation. But beneath that calm facade is a drama so intense, so extreme, that it has earned the nickname, the Supersonic Galaxy. It's the kind of object that challenges our imagination and the limits of our observational tools. It's the type of phenomenon that tells us galaxies are not static. They are dynamic, powerful, and sometimes violent participants in the cosmic story. We're about to explore this story, piece by piece, motion by motion, shockwave by shockwave. You'll learn how NGC 7619 isn't just a galaxy. It's a high-speed witness to the brutal, beautiful physics of the universe. This isn't just astronomy. This is a galaxy breaking the rules. NGC 7619 lies quietly in the night sky, nestled within the borders of the Pegasus constellation, a patch of celestial real estate named after the mythical winged horse. To the unaided eye, this region looks calm and nondescript, just another piece of the great cosmic tapestry. But hidden in that darkness, some 200 million light-years away, is a colossus moving with startling purpose. That colossus is NGC 7619. To say it's massive is an understatement. NGC 7619 is an elliptical galaxy, a vast congregation of stars, billions upon billions of them, densely packed together in an immense, egg-shaped glow of ancient light. Unlike the elegant, spiraling arms of galaxies like our own Milky Way, elliptical galaxies like NGC 7619 are smooth and nearly featureless. They're not the bright, flashy dancers of the universe. They are the quiet elders, massive and wise, shaped by age, collisions, and time. Its distance, 200 million light-years, puts it far beyond our galactic neighborhood, yet close enough in cosmic terms that we can observe it in significant detail. When we point our most sensitive instruments toward it, what we find is both majestic and violent. A galaxy that doesn't sit passively in space but rather charges through it, like a spear through thick fog. If you could sit at the center of the Pegasus constellation and look toward NGC 7619, you'd be staring into a stellar metropolis of dead and dying stars, cradled in a halo of dark matter, and surrounded by an ocean of gas that it slices through at terrifying speeds. To understand what makes this galaxy extraordinary, you must first grasp just how much material it contains. With a mass estimated to be over 100 billion times that of our Sun, it's one of the larger members of the Pegasus I galaxy group. Its stars are ancient, many formed long before the Earth existed. There's little gas left inside, which means that new stars are no longer forming. It glows not with the blue-white shine of stellar birth, but with the deep golden light of stellar age. And yet, despite this visual stillness, its motion tells another story, a story that doesn't match its appearance. Through the vacuum of intergalactic space, NGC 7619 is not idle. It surges forward at speeds so immense that the surrounding gas, unseen by human eyes, reacts to its passing. The medium between galaxies isn't truly empty. It's filled with a thin, scorching gas called the intracluster medium, and NGC 7619 is pushing through it like a spacecraft pushing through an atmosphere, leaving trails of shock-heated gas in its wake. It doesn't just inhabit space, it challenges it. What makes this galaxy even more intriguing is how it seems to embody contradiction. At a glance, it's a serene sphere of old starlight. But behind that quiet mask, there's chaos. It moves with a force that rips gas from its own body, that shapes the very medium it plunges through, that leaves traces even in the high-energy X-ray emissions we struggle to capture from Earth. It's not just a resident of Pegasus, it's one of its most compelling mysteries. From our vantage point, observing it across the eons, NGC 7619 is not just a dot of light through a telescope. It's a message from the depths of time and space. It's a whisper from an old traveler whose story is still being written. And it's only by digging deeper, into its origin, its family, and its motion, that we begin to understand how strange and wonderful this galaxy truly is. The tale of NGC 7619 begins not with a thunderous discovery, but with a quiet moment in the golden age of telescopic astronomy. The year was 1864, and astronomer Albert Marth, working from Malta under the employment of British astronomer William Lassell, was scanning the skies for faint nebulae, objects which, at the time, were mysterious patches of light in the night sky. With a 48-inch reflecting telescope, one of the largest of its era, Marth carefully catalogued these fuzzy apparitions, noting their positions and characteristics. Among them was a dim glow in the constellation Pegasus that would eventually be given the designation NGC 7619 in the new general catalogue compiled by John Lewis Emil Dreyer decades later. Back then, astronomers had no idea they were looking at entire galaxies, let alone galaxies racing through clusters at unimaginable speeds. The very idea of island universes, vast systems of stars far beyond the Milky Way, wouldn't be proven until the 1920s. So when Marth first recorded NGC 7619, it was simply another nebula, distant and undefined, existing as a soft glimmer on a hand-drawn star map. It wasn't until much later that its true nature began to unfold. As telescope optics improved and spectroscopy matured into a powerful tool, astronomers started probing the light from these strange smudges. With spectroscopy, light could be split like a prism into a spectrum, revealing the fingerprints of motion, composition, and temperature. And when the light from NGC 7619 was analyzed, it revealed something unexpected: motion. Not just motion, but rapid motion, with the telltale redshift indicating that it was not just receding due to the cosmic expansion, but also hurtling through its local cluster environment at great velocity. It was during the 20th century, especially as X-ray astronomy came into its own, that NGC 7619's hidden nature truly emerged. The Chandra X-ray Observatory, launched in 1999, was instrumental in uncovering the most dramatic clues. It wasn't just the optical light that held secrets anymore, it was the X-rays, the high-energy radiation emitted by superheated gas, that told the real story. Astronomers studying data from Chandra noticed something astonishing: a sharp edge of X-ray emission on one side of NGC 7619, and a trailing plume of hot gas stretching out behind it. This configuration was classic, an unmistakable indicator of ram pressure stripping, a process that only occurs when an object moves quickly through a denser medium. It was as if NGC 7619 was slicing through the hot intracluster gas like a speedboat through water, with a bow shock and a wake trailing in its path. It wasn't just moving, it was moving supersonically. The term, supersonic, in this context doesn't refer to sound in the way we experience it on Earth. Instead, it refers to the speed of pressure waves in the hot intracluster gas. For a galaxy to move faster than that speed is rare, and for it to produce a visible shockwave is even rarer. NGC 7619 became one of the few galaxies known to be doing exactly that. This behavior was first published and explored in depth in the early 2000s, as X-ray data from both Chandra and the earlier Rosat satellite were examined in conjunction with optical observations. The galaxy, once a mere smudge on a Victorian-era star chart, had become a subject of cutting-edge astrophysics. What Marth saw as a pale blur in the sky turned out to be a supersonic leviathan, charging through space and dragging a tail of stripped gas behind it. Its catalog number, NGC 7619, may sound dry and clinical. But the story it tells is anything but. From a 19th century discovery to 21st century revelations, it has transformed from a distant curiosity into a key to understanding the violent, dynamic environments of galaxy clusters. NGC 7619 doesn't roam the cosmos in isolation. Like most galaxies, it belongs to a larger cosmic community, a gravitationally bound group of galaxies known as the Pegasus I galaxy group. This group, located in the direction of the Pegasus constellation, is a moderately rich cluster, consisting of several dozen galaxies loosely held together by their mutual gravity and embedded in a vast halo of dark matter and hot gas. While not as densely packed as the massive Virgo or Coma clusters, Pegasus I still offers a bustling neighborhood where galactic interactions shape the fate of its members. Within this celestial family, NGC 7619 holds a prominent position. It is one of the brightest and most massive members of Pegasus I, sharing this distinction with its close neighbor, NGC 7626. These two giant ellipticals are often seen together in wide-field images of the group, like twin elders watching over their galactic kin. But their proximity is more than visual, it's gravitational, dynamic, and potentially turbulent. The Pegasus I group, like many galaxy groups, contains a mix of galaxy types, some spirals still forming stars, others ellipticals like NGC 7619 that are mostly dormant. These galaxies are immersed in the group's intracluster medium, a hot, diffuse plasma that glows in X-rays and provides a canvas against which galactic motion can paint dramatic features. The existence of this medium means that galaxies traveling through it experience pressure, much like a car driving through a strong headwind. In the case of NGC 7619, its motion through this medium is anything but gentle. NGC 7619's position near the center of Pegasus I is significant. Central galaxies and groups and clusters tend to be the oldest, most massive, and most dynamically evolved. But NGC 7619 isn't sitting still in that central spot, it's actively moving, and likely not along a straight line. The data suggest it may have fallen into the group from a peripheral orbit, accelerating as it was drawn inward by the group's gravity, reaching its current velocity as a result of this descent. That motion has consequences, not just for NGC 7619, but for the group as a whole. Its neighbor, NGC 7626, may be more than a bystander. Some astronomers have speculated that the two galaxies might be on a collision course, or that they have already experienced a close encounter in the past. Such interactions, though slow on human timescales, can have profound effects, warping halos of dark matter, disturbing the orbits of stars, and compressing gas in ways that trigger star formation, or shut it down entirely. For elliptical galaxies like these, star formation is already low, but encounters can still reheat or strip what little gas remains, or even dislodge the supermassive black holes at their cores. Beyond just its relationship with NGC 7626, NGC 7619's presence and motion through the group affect other members of Pegasus I. Its supersonic speed through the intracluster medium creates turbulence, shock fronts and pressure waves that ripple out and subtly influence nearby galaxies and the medium itself. It is, in a way, disturbing the still waters of its cosmic pond, setting up currents and waves that can affect the gas dynamics of the whole group. The gravitational forces within Pegasus I also play a role in shaping NGC 7619's path. As it moves through the group's potential well, Its motion is not linear or solitary. It responds to the pull of other massive galaxies, to the subtle tides of dark matter, and to the interactions of the surrounding gas. Each component, visible and invisible, contributes to its trajectory, turning its journey through the cluster into a complex ballet choreographed by gravity. In the big picture, the Pegasus I group is a microcosm of what happens across the universe. Groups like this are the intermediate stage between isolated galaxies and enormous clusters. Here, galaxies can still interact individually while also being subject to collective forces. In this environment, NGC 7619 becomes a case study in environmental processing, the term astronomers use to describe how a galaxy's surroundings affect its structure, composition, and evolution. By understanding NGC 7619's position in this group, and how it moves within it, we learn more about how galaxies grow old, how they interact with their neighbors, and how their fates are tied not only to what they are, but to where they are. The Pegasus I group is not just NGC 7619's address. It is its environment, its history, and ultimately, part of its identity. NGC 7619, with its smooth and seemingly unremarkable appearance, is a classic example of an elliptical galaxy, a type of galaxy that tells a very different story from the more flamboyant spirals often seen on cosmic posters and sci-fi movie backdrops. Where spirals swirl and sparkle with new stars, elliptical galaxies like NGC 7619 stand as silent sentinels of cosmic history, relics of an earlier age when the universe was more chaotic, more violent, and more formative. At a glance, elliptical galaxies seem simple, ovoid, featureless clouds of stars. But that simplicity hides a complex and evolved internal structure. These galaxies are composed almost entirely of old, evolved stars, primarily red giants and other aged stellar populations that formed billions of years ago. The telltale blue of hot, young stars is largely absent. Instead, they glow with the softer golden hue of aged light, a glow that speaks to a long and quiet retirement after an intense and active youth. What makes ellipticals like NGC 7619 distinct from their spiral cousins is the absence of organized structure. There are no grand spiral arms, no dusty lanes, no star-forming regions peppered throughout their disks. Instead, their stars orbit in random directions, forming a three-dimensional, roughly spherical or ellipsoidal shape that is more like a star swarm than a rotating disk. This randomness in stellar orbits is one of the key dynamical characteristics that defines them. The density of stars in these galaxies is immense. Unlike spiral galaxies, where stars are spread thinly across a rotating disk, ellipticals pack their stars closely, especially toward the center. NGC 7619, being a giant elliptical, has a bright and compact core with a stellar density that's difficult to comprehend. Millions of stars packed into a region only a few thousand light-years across. This central concentration is often the gravitational anchor of the galaxy, and sometimes, hidden in the heart of these dense cores, lurk supermassive black holes. Though NGC 7619's own central black hole hasn't been extensively studied, the odds are very high that one lies at its center, quietly influencing the motion of stars around it. Another defining trait is the lack of interstellar gas and dust. Gas is the fuel of star formation, and without it, the engines that power the birth of new stars grind to a halt. In elliptical galaxies, the gas has often been consumed long ago or expelled by powerful events such as supernovae, mergers, or interactions with other galaxies or the intracluster medium. NGC 7619, for example, is currently experiencing ram pressure stripping, a violent process we'll explore more later, that actively removes even the remaining gas as it plows through the Pegasus I cluster's hot plasma. With little to no gas remaining, the galaxy has effectively shut down its stellar nursery. New stars simply aren't being born anymore. This puts elliptical galaxies into a category known as red and dead, cosmic retirement homes where stars live out their remaining lifespans, slowly cooling, fading, and dying, while no new generations arise to take their place. But this stasis is deceptive. Though no longer birthing stars, elliptical galaxies are not lifeless. They are dynamically active, especially in how they interact with their surroundings. Internally, stars still orbit, light still shines, and gravity still weaves its complex web. Externally, galaxies like NGC 7619 can still experience mergers, tidal stripping, and cluster-induced effects that reshape them over time. Their size and mass also make them crucial players in the cosmic landscape. Giant ellipticals often sit at the centers of clusters or groups, serving as the gravitational hubs around which smaller galaxies orbit. Their halos of dark matter extend far beyond what we can see in optical light, influencing the motion of nearby galaxies and even affecting the distribution of gas in the intracluster medium. NGC 7619 exemplifies all of this. It is an elliptical galaxy in its most evolved form, dense, ancient, and largely quiescent. It holds the fossil record of its star-forming past within its stellar population, but shows little indication of future stellar birth. And yet, it remains in motion, not passively drifting through space but actively participating in the grander dynamics of its cluster. Elliptical galaxies are the final chapters of many galactic stories. They are what spirals and irregulars can become after long cosmic lives filled with collisions, transformations, and the erosion of star-forming fuel. They represent stability, but also finality, a stage where a galaxy ceases to grow in the traditional sense, and instead settles into long-term evolution driven by gravity and time. And in NGC 7619's case, even that quiet old age is disturbed by its movement, its stripping, and its relationship with the cosmos around it. For an elliptical galaxy, it's anything but boring. Though NGC 7619 fits neatly into the category of elliptical galaxies in form and stellar content, there's a vital twist that sets it apart. This is not a galaxy at rest. It is moving, and not just with the slow, stately drift you might expect of a massive, elderly elliptical galaxy. No, NGC 7619 is barreling through its environment at extraordinary speed. It is, quite literally, one of the fastest-moving galaxies we've observed in such a setting. This kind of motion is not typical. Most galaxies do move relative to one another. After all, everything in the universe is in motion thanks to the initial momentum from the Big Bang, local gravitational interactions, and the expansion of space. But what NGC 7619 is doing is far more dramatic than a quiet glide. It is plowing through the Pegasus I galaxy group with such velocity that it's causing visible disturbances in the hot gas that surrounds it. In other words, it's not just moving fast, it's moving fast enough to be noticed by the medium it's moving through. This alone makes it unusual. Most galaxies float serenely through the intergalactic medium, their motion only measurable through subtle redshifts and blue shifts in their spectral lines. But NGC 7619's speed is so extreme that it has observable physical consequences. It's dragging behind it a visible tail of stripped gas, like a comet streaking through the cluster's X-ray sky. The very act of moving this fast through a hot, gaseous environment has created shock structures that we can detect with specialized instruments. This is not behavior we expect from a typical elliptical galaxy. To move at such a speed requires either a tremendous gravitational slingshot effect, perhaps from a past interaction or a fall into the cluster's gravitational potential well, or the remnants of a violent merger event. Something has kicked NGC 7619 into overdrive, and that motion has placed it in rare company. Imagine for a moment the scale involved. We are not talking about an object the size of a spacecraft, or even a planet. We're talking about an object over 100,000 light-years across, containing hundreds of billions of stars, dark matter, dust, and gas, moving through the vast vacuum at more than 1,400 kilometers per second. It's like watching an entire continent-sized ship tear through the ocean, displacing everything in its path, creating shockwaves, and leaving a wake that stretches for hundreds of thousands of light-years behind it. There are few galaxies observed with similar dynamics. Some galaxies within dense clusters such as Coma or Virgo have shown signs of comparable motion, but what makes NGC 7619 stand out is the clarity of the signs, the visible evidence of its flight. It is rare for an elliptical galaxy, already so old and settled, to be seen in such a violent, energetic state. most ellipticals have settled into their environments, no longer experiencing the strong interactions that once shaped their structure. But NGC 7619 is an exception. It is alive with motion, even if the stars within it are old and quiet. And this contrast, the visual calm versus the underlying fury, is part of what makes NGC 7619 such a compelling object of study. To the naked eye or even a standard telescope, it looks like a typical elliptical, round, smooth, featureless. But look deeper, in the X-ray spectrum, in the velocity measurements, in the trail of its motion, and you begin to see the turbulence. It's a reminder that appearances can be deceiving. In the case of NGC 7619, a galaxy that looks like a quiet relic of the early universe is, in fact, a juggernaut in motion, an object cutting through its surroundings with the momentum of a cosmic avalanche. It stands apart from its peers, not just because of what it is, but because of what it's doing. And what it's doing is rewriting the story of how we think elliptical galaxies behave in a group environment. In everyday life, the idea of something going supersonic brings to mind fighter jets, booming sonic cracks, and the shattering of air's calm. We understand it instinctively. When an object moves faster than the speed of sound through a medium like air, it creates a shockwave, a disturbance that piles up and explodes outward in a burst of pressure and heat. But space is a vacuum, right? A place with no air, no sound, no shockwaves. So how can a galaxy like NGC 7619 be supersonic? The answer lies in a nuance that surprises many. Space is not completely empty. Especially not within a galaxy group like Pegasus I. Between galaxies floats a rarefied but extremely hot plasma called the intracluster medium, ICM. This gas is incredibly thin, far less dense than even the best vacuums we can create on Earth. But it's still there, and in large clusters and groups, it can reach temperatures of tens of millions of degrees Kelvin. At those temperatures, it glows in the X-ray spectrum, allowing telescopes like Chandra and XMM Newton to detect it. And where there's a medium, even a tenuous one like this, there's a speed of sound. In physics, the speed of sound isn't just a property of Earth's atmosphere. It's a measure of how quickly pressure waves travel through a medium, whether that medium is air, water, steel, or plasma. The hotter and less dense the medium, the faster the molecules within it move, and thus, the faster sound travels. In the case of the intracluster medium in Pegasus I, the speed of sound is roughly 1,000 to 1,300 km per second, depending on the local temperature and density of the gas. Now enter NGC 7619. This massive galaxy is slicing through the ICM at over 1,400 km per second, a speed faster than sound can propagate in the gas around it. That makes it supersonic, not in the traditional auditory sense, but in a very real physical one. It's breaking the local speed limit for pressure propagation, and that has dramatic consequences. Just like a jet aircraft creates a sonic boom when it exceeds the speed of sound in air, NGC 7619 creates a shock front as it barrels through the intracluster gas. This is no metaphorical ripple, it's a real, detectable structure where the gas in front of the galaxy gets compressed, heated, and shocked by the oncoming mass. Behind the galaxy, a tail of stripped material fans out, a mixture of cooler gas and turbulent wake. In X-rays, these features are visible as sharp edges, arcs, and trails, like the shock cone of a supersonic jet, but on a scale measured in tens of thousands of light-years. And unlike in Earth's atmosphere, where the effects of a sonic boom are over in an instant, the shockwave caused by a galaxy can last for millions of years, frozen in place as the galaxy continues to push through the cosmic plasma. The sound it creates isn't audible to ears, it's a propagation of heat and pressure. But in terms of energy and structure, it's just as real, and astronomers can trace its signature through careful observation. The term, supersonic, may seem poetic in space, but in NGC 7619's case, it's a technical reality. It's an acknowledgement that the galaxy isn't just drifting, it's ripping, shocking, and transforming its environment through sheer velocity. The shock front ahead of it is a visible testimony to the violence of its motion. The gas doesn't just gently flow around the galaxy. It gets rammed, compressed, and stripped. It's an intergalactic wind tunnel where NGC 7619 is the needle piercing the storm. And this process is more than just a curiosity. It's a laboratory for astrophysicists, a rare and precious opportunity to study fluid dynamics, gas physics, and galactic evolution under extreme conditions. These shockwaves reveal not only the motion of the galaxy, but the properties of the medium it's moving through, its temperature, density, and structure. By studying the supersonic motion of NGC 7619, scientists can learn about the ICM itself, how it behaves, how it influences galaxies, and how it contributes to the life cycle of galaxy clusters. So when we say NGC 7619 is supersonic, we're saying it's moving faster than the universe can communicate in its local space. It's outpacing the environment's ability to react smoothly, forcing it to respond violently. That's not just fast, it's transformative. And it's one of the reasons this galaxy, despite its quiet outward appearance, is one of the most dynamic objects in the sky. To grasp the astonishing truth that NGC 7619 is traveling at supersonic speeds through the Pegasus I galaxy group, astronomers needed more than a telescope and a clear night. They needed to extract the invisible motion embedded in light itself. To measure a galaxy's velocity, especially one as distant and massive as NGC 7619, scientists rely on a combination of techniques, particularly spectroscopy and X-ray astronomy. These tools allow them to trace the movement of stars and gas, not just across the sky, but along our line of sight, and to detect phenomena that cannot be seen in visible light at all. Let's begin with spectroscopy, a tool that transformed astronomy from a purely visual science into one of precision physics. When we split the light from a galaxy into its spectrum, essentially, breaking it down into its component wavelengths, we can see patterns of absorption and emission lines. These lines correspond to specific elements, and they occur at known wavelengths. However, when a galaxy is moving, the positions of these lines shift due to the Doppler effect. If the galaxy is moving away from us, its light is stretched, and the lines are shifted toward the red end of the spectrum, a phenomenon known as redshift. If it's coming toward us, the lines are compressed and shifted toward the blue end, or blue shift. In the case of NGC 7619, the spectral lines are significantly redshifted, not only due to the expansion of the universe, which stretches the light of all distant galaxies, but also because of its peculiar velocity, its individual motion relative to the center of mass of the Pegasus I group. This is where things get fascinating. By comparing the redshift of NGC 7619 to the average redshift of the Pegasus I cluster, astronomers can isolate how fast NGC 7619 is moving within the group, independent of the general cosmological expansion. That measurement reveals that NGC 7619 is moving at more than 1,400 km per second relative to its surroundings. This isn't merely drifting, it's speeding through the intercluster medium with extraordinary force. But while spectroscopy tells us the line-of-sight velocity, how fast the galaxy is moving away or toward us, it doesn't show the whole picture. It doesn't reveal what's happening to the gas and the environment around the galaxy. For that, astronomers turn to X-ray observations, a different kind of window into the universe. X-ray astronomy reveals the presence and behavior of extremely hot gas that is invisible to optical telescopes. In a galaxy cluster, the space between galaxies is filled with superheated plasma reaching millions of degrees, emitting X-rays as it radiates energy. When a galaxy moves through this medium, especially at high speed, it can compress and shock the gas in front of it and leave a turbulent wake behind it. These interactions are detectable in X-ray wavelengths. The Chandra X-ray Observatory, with its incredible spatial resolution, provided key observations of NGC 7619 that exposed the dynamics of this motion. What astronomers saw was startling: a sharp, curved edge of X-ray emission on one side of the galaxy and a faint, diffuse tail trailing behind it on the opposite side. This X-ray edge marks the location of a bow shock, a sudden jump in gas density and temperature, just like the shockwave ahead of a jet traveling faster than the speed of sound. This feature, known as a cold front or contact discontinuity, arises when the gas inside the galaxy meets the oncoming hot intracluster gas. The cooler, denser galactic gas is pushed backward and compressed, while the outer layers are stripped and trail behind the galaxy in a ram pressure tail. The shape and temperature gradient across this shock front allow astronomers to calculate not just the presence of motion, but its speed, direction, and physical consequences. In essence, astronomers use X-ray imaging to see the wind, to visualize the invisible intergalactic weather through which NGC 7619 is moving. And when they measure the temperature jump across the shock front and the shape of the disturbed gas, they can apply fluid dynamics equations to calculate the Mach number, the ratio of the galaxy's speed to the speed of sound in the surrounding gas. In NGC 7619's case, this Mach number is greater than 1, confirming it is moving supersonically through the Pegasus I group. Combining this with optical spectroscopy gives a more complete picture. Spectroscopy tells us how fast the stars in the galaxy are moving along our line of sight, while X-ray data shows the physical effects of that motion in the plane of the sky. Together, they converge on the same conclusion: NGC 7619 is not merely a resident of Pegasus I, it's an aggressive intruder, crashing through the environment with enough speed to leave scars in the gas around it. Interestingly, the velocity is so high that it can't be fully explained by simple orbital motion within the group. This suggests that NGC 7619 may be in the process of infalling into the Pegasus I cluster from a more distant orbit, perhaps for the first time. Or it may have recently experienced a gravitational slingshot, possibly from a close interaction with its massive neighbor NGC 7626. These types of high-speed entries are expected in hierarchical models of structure formation, where galaxies and subgroups fall into larger structures over billions of years, gaining speed as they fall into deeper gravitational wells. But it's not just about how fast it moves, it's about what that speed is doing to the galaxy. The motion is stripping away its gas, reshaping its surroundings, and possibly marking the final evolutionary stages of a once more active galaxy. NGC 7619 is a live-action display of ram pressure stripping, shockwave physics, and galactic dynamics, all rolled into one object. These measurements don't just tell us about NGC 7619, they help build a bigger picture of how environment affects galaxy evolution. By studying how motion is measured in systems like this, we gain insights into the life cycles of galaxies, the structure of galaxy groups, the temperature and density of intracluster gas, and even the distribution of dark matter, which influences all of these dynamics through its gravitational effects. NGC 7619's supersonic journey isn't just a story of speed. It's a story of how the tools of modern astrophysics, spectroscopy, X-ray imaging, fluid dynamics, can be used in concert to measure the invisible, to trace the unseen, and to reconstruct the astonishing forces that shape the largest structures in the universe. When astronomers turned their attention to NGC 7619 and began to peel back the layers of light and X-ray data surrounding this unassuming elliptical galaxy, they were met with a revelation so dramatic it changed the way we understand motion on cosmic scales. NGC 7619 isn't merely drifting or orbiting lazily within its galactic group. It is hurtling through space at a speed of over 1,400 kilometers per second. That number isn't just impressive, it's staggering. Let's try to wrap our minds around what this velocity really means. At 1,400 kilometers per second, NGC 7619 is traveling fast enough to cross the entire diameter of the Earth in less than 10 seconds. It would take less than 5 minutes to go from the Earth to the Moon. If you were traveling at that speed here on Earth, you'd circle the globe more than 35 times in an hour. But remember, this isn't a spacecraft or a rocket we're talking about. This is a massive galaxy, home to hundreds of billions of stars, an enormous dark matter halo, and remnants of interstellar gas, all moving together through the intergalactic medium with the momentum of a celestial avalanche. Even more striking, this velocity isn't just a random number. It has physical consequences for the environment it moves through. In the dense core of the Pegasus I galaxy group, the intracluster medium, ICM, a plasma composed of superheated gas that fills the space between galaxies, sets the effective speed of sound. At roughly 1,000 to 1,300 kilometers per second, depending on the local conditions. The moment NGC 7619's speed was determined to exceed that sound speed threshold, it earned a rare title among galaxies, supersonic. This supersonic designation isn't metaphorical, it has literal astrophysical meaning. As we discussed before, the concept of a sound barrier applies even in the extreme conditions of space, so long as there's a medium. And in this case, the intracluster gas, heated to tens of millions of degrees, acts as a compressible medium capable of transmitting shockwaves. When NGC 7619 moves faster than the speed of pressure waves in this gas, it doesn't simply displace the gas around it. It crashes into it, creating shock fronts, tails, and compression zones that leave visible fingerprints across multiple wavelengths of light. The galaxy's speed wasn't deduced from a single observation, it's a number cross-confirmed through redshift measurements, relative motion studies, and X-ray imaging. Spectroscopic redshift showed a high peculiar velocity, how fast it's moving with respect to the average motion of the other galaxies in the group, while X-ray images revealed the actual hydrodynamic consequences of that motion, gas piling up in front of the galaxy, and long trailing structures of stripped material behind it. One of the most significant confirmations of this supersonic motion came from analysis of Chandra X-ray Observatory data. It revealed a sharp surface brightness edge ahead of the galaxy, the signature of a cold front, which is actually a contact discontinuity formed by a galaxy's cooler, denser gas pushing into the hotter, more diffuse intracluster medium. The sharpness of the front, along with the ratio of densities and temperatures on either side, allowed researchers to estimate the Mach number of NGC 7619's motion. The Mach number, the ratio of an object's speed to the local speed of sound, was estimated to be greater than 1, confirming the galaxy's motion is indeed supersonic. In other words, NGC 7619 isn't just fast, it's moving faster than the intracluster medium can react to, meaning any pressure imbalance caused by its motion can't smooth out through simple compression waves. Instead, all that disturbance gets crumpled into a shock front that envelopes the galaxy like a high-speed bow wave. It's worth noting just how rare this is. Supersonic galaxies are not common. Most galaxies moving through clusters do so at subsonic or transonic speeds. Only a few reach and surpass that critical limit, and even fewer do so with the clarity and observational richness that NGC 7619 presents. This makes it an important case study in the effects of high-velocity galactic motion in dense environments, a phenomenon that plays a role in galaxy evolution, star formation quenching, and even the structure of the cluster itself. The velocity also raises questions about how NGC 7619 reached this speed. Was it gravitationally accelerated during a close interaction with another massive galaxy, perhaps NGC 7626, its bright elliptical neighbor? Or is it plunging into the cluster from a more distant region, its fall converting potential energy into kinetic speed as it descends deeper into the gravitational well of Pegasus I? Either scenario implies a turbulent past, rich with interaction and motion. And as it continues to fly through this hot gas, the consequences accumulate. NGC 7619 loses more of its own gas due to ram pressure stripping, reshapes the intracluster medium through compression and heating, and possibly influences the motion and orientation of other galaxies in its wake. Its astonishing velocity, over 1,400 km per second, is a number that echoes across its structure. It's in the heated rim of gas pressed against its leading edge. It's in the X-ray tails stretching behind it. It's in the silence that follows a cosmic boom we can only see, not hear. Speed in space isn't just about distance traveled. It's about what that movement does, to gas, to galaxies, to the environments they pass through. NGC 7619 is moving so fast, it's changing its own future. And the fingerprints of that speed will linger long after the galaxy has passed, embedded in the swirling hot plasma of the Pegasus I cluster like the lingering echoes of a supersonic jet, visible not as sound, but as trails of energy and matter reshaped by motion. To fully grasp the drama unfolding around NGC 7619, one must leave the realm of visible light and peer into a more energetic and violent domain, the X-ray spectrum, where temperatures soar into the millions of degrees and the normally invisible forces at play in the cosmos leave sharp, glowing scars. It is here, through the vision of the Chandra X-ray Observatory, that astronomers discovered the most striking evidence of NGC 7619's supersonic journey, a shockwave, the literal signature of a galactic-scale sonic boom. This shockwave isn't just an abstract idea or a mathematical model, it's a directly observed feature, an arc of high-energy radiation etched across the gas ahead of NGC 7619, captured by Chandra with stunning clarity. When scientists examined the X-ray data, they noticed something remarkable, a distinct, bright edge on the side of the galaxy facing its direction of motion. This wasn't a random fluctuation or an artifact. It was the compressed, heated gas of the intracluster medium being slammed by the leading edge of the galaxy as it plowed through at speeds exceeding the local sound barrier. In physical terms, this edge is a cold front, a name that might be misleading, as it doesn't imply freezing temperatures, but rather denotes a boundary where cooler, denser gas inside the galaxy meets the hotter, more diffuse gas of the cluster. But what made this cold front especially significant was its sharpness, and the temperature jump observed across it. On one side, there was gas tens of millions of degrees hot, pushed and compacted. On the other side, cooler galactic gas, seemingly held in place despite the immense external pressure. This clear demarcation is exactly what one would expect from a supersonic object moving through a compressible medium, like a bullet leaving a shock cone in air. And here's where the sonic boom analogy becomes real. In Earth's atmosphere, a jet that breaks the sound barrier leaves behind a conical pressure wave, a boom heard by those below as the wave front slams into them. In space, there's no sound in the traditional sense, but the physics is nearly identical. Instead of air, you have plasma. Instead of sound, you have pressure waves. And instead of hearing it, we see it, through X-ray emission generated as the gas is shock-heated by the galaxy's motion. This is a galactic-scale bow shock, a structure that spans tens of thousands of light-years, forming a curve in front of NGC 7619's motion that resembles the bow wave of a ship. The gas at the front is compressed and heated as the galaxy smashes into it, and behind the galaxy, a wake of stripped gas trails outward, a smoking gun of ram pressure stripping. This tail, too, glows faintly in X-rays, and contains cooler, denser material that has been peeled away from the galaxy's own halo as it tears through the cluster at over 1,400 kilometers per second. The shockwave's temperature, density, and structure have allowed astronomers to do more than just observe. They've been able to model the dynamics of the interaction. By measuring the temperature gradient across the front, they calculated how fast the gas had to be moving to cause such compression. That's how we know NGC 7619 is not just fast, it's supersonic. It's exceeding the sound speed in the surrounding medium, creating pressure discontinuities and shock fronts that tell us its Mach number, its speed relative to the speed of sound, is greater than 1. These X-ray signatures are critical for understanding the galaxy's motion in 3 dimensions. While visible light spectroscopy gives us the radial velocity, how fast the galaxy is moving toward or away from us, the X-ray shockwave tells us about its transverse motion, the part of its velocity across our line of sight. Combining these data sets allows astronomers to reconstruct the full motion vector of NGC 7619 through the Pegasus I group, providing a far more complete picture of its dynamic life. And this isn't just an isolated event. Shockwaves like this are rare, but when they're found, they reveal deep truths about both the moving galaxy and the medium it moves through. The intensity and sharpness of the shockwave around NGC 7619 indicate that the surrounding intracluster medium is dense and hot, conditions common in rich groups and clusters of galaxies. That means the shockwave also helps map the structure of the cluster itself, giving scientists insight into how matter is distributed on vast, intergalactic scales. What's particularly poetic about this discovery is that we are witnessing a moment in time, frozen in the slowness of cosmic evolution. The shockwave we see is not fleeting, it will remain visible for millions of years. It's a snapshot of kinetic violence, preserved in a form we can study, even though the sound it would make can never be heard. It's the thunder of a galaxy, recorded in light. Chandra's observations have transformed what could have been an invisible or theoretical event into a visible consequence of speed. They've shown us that even in the cold, silent expanse of space, there is turbulence. There is resistance. And when something as massive as NGC 7619 dares to defy the calm by racing beyond the physical limits of its environment, the cosmos responds, not with sound, but with fire and light. This X-ray shockwave is not just evidence of motion. It is evidence of transformation. It shows us that NGC 7619 is not simply a passive object gliding through space. It is interacting, shaping, and being shaped. It is a force in its own right, and this shockwave is the flare that marks its journey, an echo of violence carved into the very fabric of the cluster. NGC 7619 is not merely speeding through the Pegasus I galaxy group like a silent bullet, it's also undergoing a form of cosmic destruction. As this massive elliptical galaxy pushes through the hot plasma of the intracluster medium, it faces an invisible but powerful enemy, ram pressure stripping. It's a process as dramatic as it sounds, one that doesn't just affect the galaxy's motion, but deeply alters its very structure and destiny. Imagine a galaxy like NGC 7619 as a massive ship sailing through a thick fog. Only this fog isn't water vapor, it's an ocean of superheated, ionized gas that exists between galaxies and clusters and groups. While this intracluster gas is incredibly sparse by Earth standards, far thinner than any vacuum we can create, it's still there, and at the colossal speeds NGC 7619 is traveling, it begins to behave like a powerful, high-pressure wind. This is where the stripping begins. As NGC 7619 tears through this hot, sparse medium at more than 1,400 km per second, it experiences a pressure at its leading edge, a sort of atmospheric battering. That pressure is known as ram pressure, and it's not caused by gravity or magnetism, but simply by the resistance of the intergalactic gas pushing back against the motion of the galaxy. It's the same effect you'd feel sticking your hand out of a car window at high speed, except this car is a galaxy, and the wind is millions of degrees hot and stretches across millions of light years. This relentless wind slams into NGC 7619, and as it does, it begins to strip away the galaxy's gas, especially the more diffuse and loosely bound gas in the outer halo. Gas that would normally help fuel future star formation is forcibly ejected, pushed out from the galaxy's gravitational grip and left behind in its wake. This process is so effective that it leaves a long tail of stripped gas stretching behind the galaxy, like the plume behind a speeding boat. X-ray telescopes like Chandra have directly observed this phenomenon around NGC 7619. The hot gas trailing behind the galaxy glows in the X-ray spectrum, forming a visible wake. This tail is not made of stars, but of gas that was once part of the galaxy's atmosphere, material that might have cooled over time and eventually formed new stars. Now it's gone, lost to the intergalactic medium. What's left behind in the galaxy is a core that still contains old stars, but with little remaining fuel to birth new ones. This means that ram pressure stripping is more than just a mechanical process, it's an agent of galactic evolution. For a galaxy like NGC 7619, which already has the hallmarks of an elliptical, old stars, little internal gas, and no spiral arms, this stripping further solidifies its path toward cosmic dormancy. Without its gas, the galaxy loses the ability to form new stars. It becomes increasingly red and dead, a silent graveyard of ancient suns fading slowly into darkness. What's especially striking about NGC 7619's case is the clarity of this effect. In many galaxies, ram pressure stripping is suspected but difficult to observe directly. NGC 7619, however, provides a textbook example, with a sharply defined gas front, a trailing tail, and shock features that confirm the speed and violence of its journey. These observations allow scientists to study in real time how galaxies are transformed by their environments, not over millions of years, but through features visible now, across space. In a broader sense, this process is part of how galaxy clusters shape their members. A galaxy that enters a cluster isn't just caught in its gravitational web, it's subjected to environmental forces that can fundamentally alter its life cycle. Ram pressure stripping is one of the most powerful of these forces, and NGC 7619 is enduring it in full. And the implications go beyond just one galaxy. As galaxies like NGC 7619 are stripped, the gas they leave behind doesn't vanish. It can mix into the intracluster medium, enriching it with heavier elements. It may even eventually be recaptured by other galaxies, or by the cluster's central core, helping to form new generations of stars elsewhere. In this way, Ram pressure stripping is not just an end, it is also a contributor to the cosmic recycling process, redistributing material from one galactic system to the broader cluster ecosystem. So while NGC 7619 presses forward, shedding its outer layers into space, it tells a story that is both destructive and regenerative. The galaxy is losing part of itself, yes, but in doing so, it is feeding the cluster, altering its own fate, and giving astronomers a rare, clear view into one of the most powerful and transformative processes in the universe. To picture what's happening to NGC 7619 as it blazes through the Pegasus I group, imagine something closer to Earth. A wind tunnel, the kind used to test the aerodynamics of race cars or fighter jets. In these controlled chambers, objects are placed in the path of a fast-moving airstream, allowing scientists to study how air flows around them, where turbulence forms, and where structural strain develops. Now scale that concept up vastly. Instead of a car, think of a massive elliptical galaxy. Instead of a tunnel, picture a medium of searing, thin plasma filling the space between galaxies. And instead of air, think of hot, million-degree gas rushing past at supersonic speed. That's the environment NGC 7619 is speeding through. This analogy, a galactic wind tunnel, is no exaggeration. As NGC 7619 moves at over 1,400 km per second, the intracluster medium doesn't gently part to make way for it. Instead, the gas crashes into the galaxy's leading edge, piling up, compressing, and pushing against it with tremendous force. From the galaxy's frame of reference, it isn't moving through the cluster is attacking it, battering it with a high-velocity stream of energy and particles. This wind isn't just intense, it's transformative. It generates drag, it reshapes the galaxy's gas profile, and it causes material stress. The gas in the galaxy's outer regions, particularly the lower density, loosely bound material, can't withstand the onslaught. It begins to flow backward, trailing behind the galaxy in streamers and wisps, forming a visible tail in X-ray wavelengths. The result is a structure remarkably like a smoke trail in a wind tunnel, curling and stretching in the wake of the object that caused it. But this galactic wind is different from wind on Earth in another important way. It's invisible to the naked eye. It's only through instruments like the Chandra X-ray Observatory that we can see it. And what those images show is stunning. The compressed gas at the front of NGC 7619 glows brighter in X-rays due to its increased density and temperature. The stripped material behind it appears as a diffuse, elongated structure, evidence of how much mass is being lost to the storm. The shape of this tail can even tell astronomers something about the nature of the surrounding medium. If the gas is turbulent, the tail may appear irregular or twisted. If it's relatively smooth and uniform, the tail will look more coherent and streamlined. In either case, the very presence of such a tail is a smoking gun, an unmistakable sign that NGC 7619 is interacting directly, physically, and forcefully with the environment it moves through. This galactic wind tunnel also explains why the galaxy develops such sharp boundaries. The leading edge of the galaxy acts like a heat shield, compressing the plasma in front of it into a dense, hot region. Behind that edge, the stripped gas cools slightly and begins to diffuse. The result is a bow-like structure on the forward side of the galaxy, and a plume on the rear, a classic aerodynamic profile, scaled to galactic proportions. What's fascinating is that despite the harshness of this environment, the stars themselves remain largely unaffected. Stars are so massive and tightly bound by gravity that the intracluster medium can't strip them away. They pass through the galactic wind largely unscathed. But the gas, especially the cold, star-forming gas in the galaxy's halo, is much more vulnerable. It's this gas that's peeled away layer by layer, altering the galaxy's future. This loss is permanent. Once that gas is gone, it's unlikely to be recovered. Unlike wind blowing leaves from a tree, where the leaves might settle nearby, the stripped gas of NGC 7619 is carried far downstream, heated and mixed into the cluster's vast reservoir. It no longer belongs to the galaxy. It has become part of the larger environment. In this way, the galactic wind tunnel isn't just an observational metaphor, it's a mechanism of transformation, a tool by which the cluster environment sculpts its member galaxies. And it's not a unique story. Ram pressure stripping and wind-like interactions happen in many clusters and groups, but NGC 7619 is a particularly vivid example. Its speed, orientation, and the density of the medium through which it travels all combine to produce a textbook case of stripping and turbulence. For astrophysicists, it's an invaluable laboratory, a natural experiment running on a cosmic scale, revealing how galaxies are not just shaped internally by the stars they form, but externally by the space they move through. In this way, NGC 7619 becomes more than just a fast-moving elliptical galaxy. It becomes a probe, a test particle feeling the physical texture of its environment. As it moves, it writes its story into the gas around it, not with ink, but with heat, pressure, and motion. Its trail becomes a record of its journey, a visual echo of the forces it has endured. And like a ship caught in an endless storm, NGC 7619 doesn't slow down. It continues forward, the wind at its bow, the wake widening behind. It's a lonely, relentless voyage, one shaped not by collision, but by exposure. The longer it travels, the more of itself it sheds. But in doing so, it tells a story we would never have seen otherwise, the story of how space, though silent, is never still. To truly understand what's happening to NGC 7619, how it's not just moving but transforming, we must look beyond visible light. We need to observe in the X-ray spectrum, where the true drama of the galaxy's high-speed plunge through the Pegasus I cluster comes to life. Fortunately, telescopes like NASA's Chandra X-ray Observatory allow us to do just that, and what they reveal is nothing short of spectacular: shock fronts, heated gas, and long, glowing tails that trace the scars of a galaxy under assault. In optical images, NGC 7619 might appear serene, a luminous, elliptical galaxy with a soft halo and no apparent disturbance. But switch to X-ray, and a very different image emerges. Suddenly, the galaxy is not isolated. It's enveloped in a glowing cloud, its leading edge flaring brightly, and a wispy trail extending far behind it. These aren't just pretty pictures. They are smoking gun evidence of the violent interaction between the galaxy and the intracluster medium it's charging through. Chandra's incredible resolution lets astronomers dissect this interaction in detail. One of the most prominent features visible in X-ray data is a sharp surface brightness discontinuity on the front edge of the galaxy. This is where the galaxy's own gas, colder and denser, slams into the hot, thin plasma of the cluster, producing a compressed region that glows more intensely in X-rays. This interface, called a cold front, forms a boundary between the galaxy's atmosphere and the oncoming stream of intracluster gas. Despite the name, the temperature of this front is anything but cold. Temperatures on both sides are in the tens of millions of degrees, but the denser gas in the galaxy retains lower entropy compared to the hotter, more diffuse ICM. Just behind this bright leading edge, Chandra also detects a long, tapering tail of X-ray emission, a signature of gas that's been stripped from NGC 7619 as it rams through the cluster. This tail isn't static. It is a fluid, reactive trail, shaped by turbulence, pressure gradients, and the momentum of the galaxy itself. It contains gas that was once part of NGC 7619's halo, perhaps gas that would have cooled and condensed into new stars. But now, it has been forcibly removed and heated to the point where it emits X-rays. It will not be forming stars anymore. Instead, it is recycled into the larger cluster environment. But there's more. X-ray spectroscopy, another powerful tool, allows astronomers to measure the temperature and metallicity, the abundance of heavy elements, in different parts of the gas. What they find is that the strip tail often contains enriched material, elements like oxygen, iron, and silicon, that were forged in the interiors of stars within NGC 7619 and later expelled into its halo through supernovae. This means the stripped gas is not only hot and glowing, it's chemically distinct, a trail of history documenting the internal life of the galaxy now mixing with the wider cosmos. In addition, the presence of turbulence and instabilities within the tail can be inferred from the structure and brightness fluctuations. Some parts of the gas plume are narrow and smooth, while others ripple, suggesting complex dynamics, eddies, vortices, and shear flows, like the disturbed air behind a jet's wing. These patterns help scientists understand how gas behaves when stripped at high speeds, and how long the stripped material can remain coherent before being fully mixed into the intracluster medium. The contrast between the sharply defined front and the diffuse trailing tail is also instructive. It shows that the galaxy's core remains intact, a region where gravity is strong enough to hold on to gas and stars despite the onslaught. But farther out, where the gravitational pull weakens, gas is swept away. This gradient of stripping is visible in X-rays, turning the galaxy into a layered model of how external forces strip galaxies from the outside in. Perhaps most astonishingly, X-ray maps can show the temperature gradient from front to tail. Gas at the leading edge is significantly hotter, the result of being compressed and shock heated by the galaxy's motion. Farther back in the tail, the gas is cooler, having expanded and radiated away some of its heat. This temperature distribution is not random, it's a thermodynamic map of NGC 7619's journey, allowing astrophysicists to track not just where the galaxy is, but what kind of resistance it's facing, and how violently it's losing material along the way. These observations make NGC 7619 a case study in ram pressure physics. It's not just a fast-moving galaxy, it's a laboratory for high-energy astrophysics. The detail and structure revealed in X-ray allow for the calibration of models that predict how galaxies evolve when they enter cluster environments. And this is crucial because many galaxies go through this process. In fact, it's one of the main mechanisms by which spiral galaxies are transformed into ellipticals over time, by falling into clusters, getting stripped of their gas, and slowly fading into quiescence. So, while a visible light telescope might show NGC 7619 as silent and still, X-ray eyes reveal something very different, a chaotic battlefield, with heat, turbulence, and stripping all in progress. The galaxy isn't floating peacefully. It's in a state of high-energy interaction, surrounded by a cocoon of its own discarded gas, etched in light too energetic for human eyes to see. It's through this lens, through Chandra's piercing vision, that we come to understand the true power of motion in space. Not just how fast something moves, but how profoundly that motion affects its structure, its composition, and its future. NGC 7619 is a witness to this, and its X-ray glow is a confession. It has been through a war that left no sound but left behind trails of light. Behind the luminous, dense heart of NGC 7619, stretching like a long and fading whisper into the surrounding intracluster medium, lies one of the galaxy's most haunting features, its tail of stripped gas. It is not composed of stars, nor is it visible in ordinary optical wavelengths. Instead, it is a glowing, ethereal trail, hot, diffuse plasma pulled from the galaxy's halo and body as it careens through space at over 1,400 kilometers per second. And while stars in the galaxy remain untouched by the cluster's invisible winds, this gaseous tail tells a very different story, one of disruption, loss, and violent motion. To the untrained eye, this tail might look like nothing at all. But to astronomers peering through X-ray telescopes, it's a signature, a celestial fingerprint, of supersonic travel through a medium dense enough to fight back. The tail itself is the product of ram pressure stripping, where the fast-moving galaxy pushes against the intracluster gas, and the resulting pressure forces its own gaseous halo backward, out of its gravitational grasp. That gas, no longer anchored to the galaxy, lingers behind it in a trail that can stretch across tens of thousands of light-years. The structure of this tail is both beautiful and informative. It begins narrow, tight, and relatively bright just behind the galaxy's core, and gradually fans out into a more diffuse, fainter stream. This morphology tells us a lot. Near the galaxy, the stripped gas is still compact, not yet fully mixed with the hot medium around it. Farther out, the tail widens as turbulence and diffusion take over. At these larger distances, the gas becomes less dense, cooler, and more chaotic, slowly blending into the rest of the Pegasus I group's environment. It is a trail of decay, a map of material that once belonged to NGC 7619 but now drifts, unanchored, into the intergalactic dark. This tail is not just an incidental feature, it is a diagnostic tool. Its length, shape, and brightness tell us about the velocity of the galaxy, the density of the cluster medium, and the composition of the stripped gas. In NGC 7619's case, the tail confirms the galaxy is not just moving fast, it is losing mass rapidly and violently. The brighter sections of the tail near the galaxy show regions of higher density, likely made up of gas that was more tightly bound and therefore took more pressure to dislodge. These sections emit more X-rays, lighting up under Chandra's gaze like sparks trailing from a meteor. But as we move farther from the galaxy's core, the gas becomes more diffuse. It glows less brightly, but it remains detectable, an echo of energy, cooling as it travels, still shaped by the wake of the galaxy's motion. Here, instabilities begin to form. These are not just passive clouds. They ripple and curl, revealing the complex fluid dynamics at play between the galaxy's expelled material and the surrounding ICM. It's a form of cosmic weather, sculpted by wind shear, thermal pressure, and turbulent eddies. This is also where astronomers begin to see the mixing process in action. As the tail stretches on, Kelvin-Helmholtz instabilities, tiny ripple-like structures, can appear at the interface between the galaxy's expelled gas and the surrounding medium. These indicate where the two fluids are rubbing against each other, gradually merging. It's a subtle process, one that takes millions of years, but it ensures that the gas NGC 7619 loses doesn't simply sit in space. It becomes part of the larger cluster ecosystem. Spectroscopic studies have even revealed something more remarkable. This trailing gas is enriched with heavy elements, iron, oxygen, and other metals forged in the hearts of stars and expelled through stellar winds and supernovae. This makes the tail a chemical signature, a ribbon of evidence that NGC 7619 has lived a long, active past, one where stars formed, aged, and died, returning their processed material to the galaxy's gaseous halo. Now, that enriched gas is being donated to the cluster itself. It's not just the loss of raw material for star formation, it's the export of history, scattered into space by motion alone. The geometry of the tail is also a clue to the galaxy's trajectory. Since the tail points directly away from the direction of motion, it acts as a natural compass, letting us trace NGC 7619's path across the cluster. This is vital for reconstructing the galaxy's orbit, its speed, and its interactions with nearby systems. It even provides hints about past encounters, perhaps with other galaxies like NGC 7626, or its recent infall into the Pegasus I cluster, which may have triggered this phase of intense stripping and rapid motion. Unlike spiral galaxies, which often show disrupted arms and starbursts as a result of interactions, elliptical galaxies like NGC 7619 are more structurally rigid. They don't show obvious external deformations. So tails like this become the indicator of disturbance. They whisper of forces invisible in the optical band, forces that shape and evolve galaxies silently, leaving no trail but a glowing vapor of high-energy plasma. It's easy to forget how vast these structures are. Even a relatively short tail in galactic terms might stretch across 100,000 light-years or more, longer than the diameter of the Milky Way. And yet they are feather-light compared to the galaxy itself. They are composed of diffuse gas, tenuous and transparent, and only visible through dedicated, sensitive instruments. But what they represent is far more than mass loss. They are trophies of motion, testimonies of survival in an unforgiving environment. In NGC 7619, the tail is the galaxy's autobiography, written not in words but in light, heat, and motion. It tells us that the galaxy is not drifting quietly through the universe, but forging ahead in a battle with its surroundings. It is shedding weight, evolving, and possibly being reshaped permanently. And it invites us to watch, to study, and to understand that even in the vastness of space, nothing moves without leaving a trace. When galaxies like NGC 7619 reach extraordinary velocities, speeds so great they surpass the sound speed of their environment, they enter a regime of physics that is both rare and transformative. In Earth-based terms, we call this breaking the sound barrier. But in the cosmos, this event doesn't produce an audible boom, it creates shockwaves, compressed plasma, and violent thermodynamic transformations. The physics of a supersonic galaxy is no mere metaphor. It's a real, measurable phenomenon where energy, momentum, and matter interact in ways that reshape the galaxy and the space around it. To understand this, we need to first redefine sound in the context of intergalactic space. Unlike sound in air, which is a mechanical wave traveling through molecules at hundreds of meters per second, sound in the intracluster medium, ICM, is a pressure wave traveling through a plasma at speeds that can reach up to 1,000 to 1,500 kilometers per second, far faster than anything on Earth. This speed is determined by the temperature and density of the gas. The hotter and more ionized the medium, the faster sound travels through it. Now consider a galaxy like NGC 7619, which is moving at speeds around 1,400 kilometers per second, right in the zone, or even slightly beyond, the local sound speed in the Pegasus I cluster. That means NGC 7619 is not just moving through space, it is disrupting it. Like a jet fighter crossing the sound barrier, it's creating a shock front ahead of it. The gas in front of the galaxy doesn't have time to get out of the way. Instead, it is rapidly compressed, heating up as it's squashed into a dense, high-pressure wall. This is not a smooth transition. It's abrupt, with dramatic jumps in density, temperature, and pressure, the hallmarks of a supersonic shockwave. These shock fronts act like galactic-scale pressure cookers. The sudden compression of gas heats it to tens of millions of degrees, causing it to emit X-rays, which we detect with instruments like the Chandra X-ray Observatory. These emissions reveal exactly where the shock is forming, how strong it is, and how much energy the galaxy is pumping into its surroundings simply by moving. One of the most interesting physical effects of supersonic travel through plasma is the development of Mach cones, analogous to the sonic boom cone generated by supersonic aircraft. In theory, if a galaxy moves faster than the speed of sound in the cluster medium, it should produce a cone of compressed gas behind it, marking the region affected by its supersonic wake. In practice, this cone can be hard to detect directly due to the complexity of cluster environments, but simulations and observations together confirm its presence in systems like NGC 7619. This interaction also changes the hydrodynamic stability of the galaxy's atmosphere. The outer gas layers are no longer in equilibrium. Instead, they are stripped by the intense ram pressure, forming tails, vortices, and instabilities. These structures aren't just pretty features. They reveal how the laws of fluid dynamics play out at immense scales. The plasma behaves like a fluid, and the interface between the galaxy's cooler gas and the hotter ICM becomes a turbulent zone. In this region, Kelvin-Helmholtz instabilities may arise, creating ripple-like structures that help mix the stripped gas into the cluster environment. Supersonic motion also affects entropy distribution. The gas in the leading edge of the galaxy is compressed and heated, raising its entropy, while cooler, stripped gas in the tail may temporarily retain lower entropy values. This gradient can be used to infer motion direction, speed, and even the history of the galaxy's interaction with its surroundings. NGC 7619, with its sharp cold front and long X-ray tail, provides a vivid example of such entropy variations in action. Another fascinating aspect of supersonic galaxy physics is that it leads to energy dissipation in the ICM. As the galaxy plows through, it doesn't just displace gas, it transfers kinetic energy to it. This heats the surrounding medium and contributes to the overall thermal energy budget of the cluster. Over time, the repeated passage of galaxies like NGC 7619 may help keep the ICM hot, preventing it from cooling and forming stars in the cluster core. This process, though indirect, is part of the broader feedback mechanisms that regulate galaxy and cluster evolution. Supersonic motion also influences the magnetic field structure of the ICM. As plasma is compressed at the shock front, the local magnetic fields are also compressed and intensified. These fields can wrap around the strip tail, or form boundary layers that confine the expelled gas. Though harder to observe directly, radio observations sometimes reveal synchrotron emission from relativistic electrons spiraling along these field lines, offering a glimpse into the magnetic turbulence stirred up by galaxies in motion. And then there's the matter of momentum transfer. As NGC 7619 loses gas, that material doesn't vanish, it carries momentum away from the galaxy. This exchange means the galaxy's mass distribution and even its future trajectory may be altered subtly over time. While not enough to dramatically change its orbit, this mass loss can redistribute internal gas flows and change the balance of forces within the galaxy, influencing how it settles into its eventual, stripped-down state. Supersonic galaxies like NGC 7619 also serve as natural laboratories for testing theoretical models. Astrophysicists run massive computational simulations to replicate the motion, shock formation, and gas stripping processes. These simulations are calibrated using real data from galaxies like NGC 7619, making each observation a key piece in understanding not just one galaxy, but how thousands of others may behave under similar conditions. All of this leads to a profound realization: in the vast, silent void of space, speed has consequences. When a galaxy like NGC 7619 moves fast enough to break the sound barrier of its environment, it's not just about velocity, it's about interaction, transformation, and feedback. The surrounding gas resists, pushes back, reshapes the galaxy, and leaves behind luminous evidence of that struggle in the form of glowing shock fronts, stripped tails, and heated plasma. And even though no one can hear it, the physics of sound is very much alive in space. It moves not through pressure waves you could sense with your ears, but through thermodynamic shifts and radiation. Galaxies like NGC 7619 don't shout, but the universe still listens, and the light they leave behind tells a story louder than any boom ever could. The incredible speed of NGC 7619, hurtling through space at more than 1,400 kilometers per second, is not just a curious number, it's a mystery. In a universe where most galaxies drift quietly within their clusters, pulled along by the slow dance of gravity, NGC 7619 is a cosmic sprinter. But why? What force could have launched an entire galaxy, containing hundreds of billions of stars, dark matter, and gas, into such a fast-paced trajectory through the Pegasus I cluster? The answer lies in the deep gravitational dynamics of galaxy groups and clusters, regions where mass is not just concentrated, but colliding, merging, and reshaping on cosmic scales. Galaxies do not exist in isolation. They are constantly under the influence of nearby galaxies, dark matter halos, and even the collective mass of entire clusters. In the case of NGC 7619, its supersonic speed is likely the result of gravitational interactions, possibly involving a combination of cluster infall, multi-body dynamics, and even a past collision. One plausible explanation is that NGC 7619 is currently undergoing infall into the Pegasus I group. Galaxy clusters and groups are not static. They're still growing, still pulling in smaller galaxies and galaxy groups from their surroundings. As NGC 7619 fell inward toward the dense core of the Pegasus I cluster, it would have accelerated due to the immense gravitational pull of the cluster's mass. This infall process acts like a cosmic roller coaster. As the galaxy plunges into the potential well of the cluster, it gains speed, sometimes to extreme levels. In this model, NGC 7619's speed is simply a result of where it is in its descent, near or past the pericenter of its orbital motion, where velocity peaks. Another possibility involves gravitational slingshot effects, what physicists call three-body interactions. In the dense environments of galaxy groups, it's not uncommon for close encounters between multiple galaxies to produce significant changes in velocity. If NGC 7619 passed near a more massive companion, Perhaps its neighbor, NGC 7626. The gravitational tug-of-war could have flung it forward, imparting a burst of momentum in a specific direction. Such interactions don't require direct collisions. Even a close pass can redistribute momentum, sending one galaxy careening ahead while the other slows down. If NGC 7619 experienced this kind of interaction early in its history within Pegasus I, it could explain its current motion and its orientation within the group. Yet another theory is more dramatic: a past collision or major merger. If NGC 7619 once collided with a smaller galaxy, or even with another elliptical, it could have experienced a complex set of forces that reshaped its motion entirely. During galactic collisions, the stars themselves rarely smash into one another, but the gravitational fields of the galaxies interact strongly, especially if the masses are comparable. These tidal forces can distort or eject gas, shift orbital paths, and, in rare cases, launch one of the galaxies on a high-speed trajectory. While NGC 7619 currently shows no obvious visual signs of a recent merger, that doesn't rule one out. Elliptical galaxies, especially massive ones, often show smooth outer profiles even after a merger has taken place, because they can rapidly settle back into a stable shape. The only lingering clues might be found in the motion of stars within the galaxy or the properties of its central core. There's also the possibility that dark matter plays a significant role in this dynamic. Galaxy clusters contain huge, invisible halos of dark matter, mass that doesn't emit light but exerts gravity. These halos define the gravitational landscape of the cluster. If NGC 7619 fell through or near a particularly dense region of dark matter, say, the overlapping halos of multiple galaxies, it could have been accelerated in ways that are difficult to trace with light alone. Since we can't directly observe dark matter, these interactions are speculative but strongly supported by simulations. They show that galaxies can reach high velocities simply by falling into deep potential wells formed by dark matter concentrations. Another key point is that NGC 7619 is likely not alone in its journey. Its neighboring galaxy, NGC 7626, shows signs of motion and interaction as well, suggesting that the two may have entered the cluster environment together as part of a bound pair or subgroup. As they fell into Pegasus I, their mutual gravitational tug, combined with the cluster's pull, could have twisted their paths and accelerated them in tandem. In this scenario, their high speeds are not isolated flukes, but rather signatures of a larger cosmic event, the accretion of a smaller galaxy group into the larger Pegasus I structure. It's also worth noting that such high velocities are more likely to be preserved in elliptical galaxies like NGC 7619 because they're structurally robust. Spirals, with their delicate arms and large gas disks, tend to be disrupted by such motion, losing their form. But ellipticals, being more compact and less dependent on gas for their structure, can barrel through the cluster medium, keeping their shape while still being transformed from the inside out. So, why is NGC 7619 moving so fast? Likely because it's a veteran of gravitational war zones, pulled, tossed, and flung by the combined mass of galaxies, groups, and clusters. Whether it was accelerated by a fall into Pegasus I, hurled by a three-body interaction, launched by a past collision, or dragged through invisible tunnels of dark matter, one thing is clear: its speed is no accident. It's the result of billions of years of cosmic interaction, of invisible hands pushing and pulling across unimaginable distances. And in this motion, NGC 7619 becomes a witness to the dynamic, ever-changing universe. It shows that galaxies are not just passive collections of stars. They are players in a massive gravitational ballet, sometimes flung to astonishing velocities as the music of the cosmos swells and shifts. Its path, its tail, and its shock front are all chapters in that story, written not with ink but with motion, energy, and silence. Despite the chaos surrounding NGC 7619 as it slices through the Pegasus I cluster at supersonic speed, leaving behind glowing trails of stripped gas and shock-heated plasma, one part of the galaxy remains almost eerily unaffected: its stars. These ancient, brilliant beacons, numbering in the hundreds of billions, continue to orbit the galaxy's center of mass, virtually unaware of the violent struggle between the galaxy's gas and the intracluster medium that plays out around them. This disconnect is one of the most striking aspects of galactic motion through space. While gas is highly susceptible to external forces like ram pressure, shock compression, and turbulence, stars are comparatively immune. They are compact, massive, and bound tightly by gravity to the galaxy's core. The intergalactic plasma that strips away hot gas from a galaxy simply doesn't exert enough force to move or dislodge stars from their orbits. Why is that? To understand, consider the relative sizes and masses of the components involved. A single star, like our Sun, is a dense, self-contained body with significant inertia. The intracluster medium, by contrast, is incredibly tenuous. Even though it can reach temperatures of tens of millions of degrees, it's so diffuse that a cubic meter contains just a few particles. The ram pressure from this medium is more than enough to strip away wispy halos of hot gas, but it barely registers as a force on something as dense and compact as a star. Additionally, the stars in NGC 7619 are moving incredibly fast in their own right. Orbital speeds around the galactic center can reach hundreds of kilometers per second. This internal motion means that even if there were some external nudging from the cluster's hot gas, it would be completely drowned out by the star's gravitational binding to the galaxy. Essentially, the stars are locked into place, held by the collective gravity of the entire galactic structure. The result is that while the gaseous envelope of NGC 7619 is ripped away in a blazing X-ray tail, the stars continue to orbit undisturbed. There's no noticeable stripping of stars, no scattering of the stellar population into intergalactic space, at least not from the ram pressure alone. In fact, if one were to observe NGC 7619 in visible light alone, ignoring the X-ray data, it might look almost undisturbed, its spherical or elliptical shape intact, its stars quietly glowing as if nothing at all were happening. Of course, this doesn't mean the stars are entirely unaffected by NGC 7619's journey through space. While the intracluster medium can't directly push them around, other processes set in motion by the galaxy's supersonic plunge could influence their long-term dynamics. One indirect effect is gravitational. If NGC 7619 loses a significant amount of mass, primarily in the form of gas, the galaxy's gravitational potential changes. This shift might slightly alter the orbits of some stars, especially those in the outer halo, which are more loosely bound. These changes wouldn't be catastrophic. They wouldn't eject stars or destroy the galaxy's structure, but over millions of years, they could cause subtle rearrangements in the galaxy's stellar halo or outer envelope. Another possibility involves central dynamics. NGC 7619, like many massive ellipticals, may host a supermassive black hole at its center. If the galaxy has had past interactions, say, a gravitational encounter with NGC 7626 or a minor merger, those events could set off sloshing motions in the galaxy's core. These can, over time, heat the stellar population and cause changes in the velocity dispersion of stars. But these effects would be gradual and internal, not directly related to the ram pressure or the high-speed motion through the cluster. Moreover, in denser regions of clusters, tidal interactions can occur between galaxies, gravitational tugs that can distort galaxies and, in rare cases, strip away stars. But NGC 7619, at least at present, shows no strong signs of such distortions. Its stellar body remains intact, suggesting that while it may be experiencing some gravitational interactions within Pegasus I, none have been powerful enough to disrupt its stellar population. It's also important to note the age of the stars in NGC 7619. As an elliptical galaxy, it's dominated by old, red stars, formed billions of years ago during an early epoch of intense star formation. These stars are not forming anymore, and they don't rely on the gas being stripped away to continue shining. So while the galaxy is losing its future, its ability to create new stars, it's not yet losing its present. The stars that exist now will continue to burn for billions of years, slowly aging in their elliptical cradle. In this way, NGC 7619 becomes a paradox. It's a galaxy under siege, losing gas, radiating heat, and lighting up the cluster in X-rays. Yet from the inside, for its stars, it's business as usual. The galaxy remains gravitationally cohesive, its stars orbiting in stately ellipses, ignorant of the violent stripping happening just beyond their reach. It's a cosmic illusion. The stars shine calmly, the galaxy seems serene, but the truth lies in wavelengths we can't see with the naked eye. It's a galaxy in turmoil, hidden beneath a placid exterior. The storm rages outside the star's awareness, but it's a storm that will shape the galaxy's fate for billions of years to come. While the stars of NGC 7619 carry on in silence, unaffected by the cosmic tempest raging around them, the same cannot be said for the gas that once filled the galaxy's outer regions. That gas, diffuse, hot, and vital, is now being torn away, stripped off in long glowing tendrils, scattered into the Pegasus I cluster. And with every molecule of gas lost to the intracluster winds, the galaxy moves one step closer to stellar sterility. This isn't just a dramatic visual event, it's a fundamental transformation. It marks the end of star formation, the closing of a chapter, and the beginning of a long, slow decline into galactic dormancy. Gas is the lifeblood of a galaxy. It serves as the raw material from which new stars are born. In spiral galaxies, it condenses into cool, dense molecular clouds, stellar nurseries that give birth to brilliant young suns. But even in ellipticals like NGC 7619, which are already relatively quiescent, the presence of hot gas halos plays a crucial role. This gas cools slowly over time and can still form stars in rare instances or maintain the pressure balance that helps preserve the galaxy's internal structure. When that gas is stripped away, star formation doesn't just slow, it stops. The process is brutally efficient. As NGC 7619 moves at supersonic speeds through the Pegasus I cluster's dense intracluster medium, it experiences a phenomenon known as ram pressure stripping. The gas inside the galaxy, especially the hot, ionized halo that extends well beyond the visible stars, feels the force of this wind. Unlike stars, the gas is not gravitationally bound as tightly, and it behaves like a fluid, responding to external pressure by flowing, compressing, and eventually being peeled away. The outermost gas is the first to go. As the galaxy plows forward, this gas is compressed at the leading edge, heated, and then pushed backward by the oncoming stream of cluster plasma. Once this gas is pushed beyond the gravitational grip of the galaxy, it's lost forever, trailing behind in long tails that glow in X-rays. The inner regions may resist longer, but even they aren't immune. Over time, as the galaxy continues to lose its reservoir of halo gas, the inner pressure drops, and the galaxy can no longer retain even moderately bound gas. But it's not just the hot gas halo that's at risk. Even residual amounts of cooler gas, the kind that might someday form stars, are eventually stripped or evaporated due to thermal conduction and mixing with the hotter ambient medium. The stripped gas is immersed in a sea of superheated plasma. It's like throwing an ice cube into boiling water. Any cool gas that remains is quickly heated, ionized, and dispersed, no longer capable of coalescing into stars. This loss has far-reaching consequences. Without gas, star formation ceases entirely. NGC 7619 may have already formed the vast majority of its stars billions of years ago, but galaxies are long-lived systems. Even a small amount of residual star formation can affect a galaxy's brightness, color, and structure over time. Removing this ability cements the galaxy's fate. It becomes what astronomers call a red and dead galaxy, dominated by aging, red stars, with no fresh generations to rejuvenate its glow. There's another layer of loss as well, the chemical memory carried by the gas. Much of the halo gas in galaxies like NGC 7619 is enriched by supernova explosions, filled with elements like iron, oxygen, and carbon that were forged in the hearts of stars. This gas, had it remained, could have seeded the next generation of star formation with metals. But now, expelled into the intracluster medium, it's no longer part of the galaxy's evolution. It's been donated to the wider cluster, contributing to the diffuse gas between galaxies rather than the structure of the galaxy itself. And as the galaxy loses gas, it doesn't just lose its potential, it loses part of its thermal and dynamic balance. Hot gas in the halo helps stabilize the galaxy against gravitational collapse. When that gas is stripped away, internal motions may shift. There may be reduced thermal pressure, leading to changes in the density distribution or the formation of subtle structural features as the remaining stellar population adjusts. The galaxy becomes colder, not just in temperature, but in behavior, a quiet relic, coasting toward gravitational senescence. One might ask, could the gas ever return? Could NGC 7619 accrete new material from the surrounding medium? The answer is grim. In the heart of a cluster, the odds are overwhelmingly against it. The environment is too hot, too dynamic. Any gas the galaxy encounters will be at temperatures of millions of degrees, far too hot to be captured or cooled effectively. Instead of gaining new material, NGC 7619 is more likely to continue losing what little remains. What makes this even more tragic, in cosmic terms, is that galaxy clusters like Pegasus I are often the graveyards of star formation. They are rich in gas, yet poor in star-making potential, not because they lack the material, but because the gas is so hot and energetic that it refuses to settle. Galaxies that fall into these environments are often doomed to fade, robbed of their star-forming lifeblood, surrounded by a sea of unattainable fuel. So, as we peer into the glowing X-ray tail of NGC 7619 and watch the stream of gas trail behind it, what we're really seeing is the future being stripped away. Every tendril of glowing plasma is a lost opportunity, an aborted star, a dimmed cluster, a silenced light. The galaxy, once full of potential, is now on a one-way path to quiescence. Not because it ran out of time, but because the universe around it forced it into stillness. This is the cost of speed. The faster NGC 7619 moves, the more it sheds, the more it transforms. And though the stars remain for now, glowing like embers in the night, the fire that once created them is gone, torn away, scattered across space, never to return. NGC 7619 offers us a breathtaking window into the evolutionary journey of galaxies, playing out in real time across hundreds of millions of light years. It is not just a solitary body speeding through the Pegasus I cluster, it is a vivid, real-world case study in how environmental interactions shape galaxies. If we want to understand how galaxies live, transform, and eventually grow quiet, NGC 7619 becomes one of the most compelling examples in the cosmic catalog. At first glance, elliptical galaxies like NGC 7619 might seem inert, frozen in their final form. They're often described as old, red, and passive, galactic retirement homes for stars that were born billions of years ago. But such assumptions are deceptive. Beneath that calm surface is a history of violence, transition, and survival, and NGC 7619 is still evolving today, not through internal processes, but through external pressures. Galaxies are not isolated islands. They are shaped as much by their surroundings as by their internal structure. And clusters like Pegasus I are harsh environments, regions packed with hot plasma, gravitational turmoil, and frequent galactic encounters. When a galaxy falls into such an environment, especially at supersonic speed, the consequences are dramatic. NGC 7619 shows us what happens when a galaxy enters the lion's den, a rich, gaseous cluster core, where it must navigate an ocean of obstacles, quite literally fighting for its structure and future. As NGC 7619 barrels through the intracluster medium, it experiences multiple evolutionary pressures at once. The most obvious is ram pressure stripping, that relentless wind of hot plasma slamming into the galaxy's gas. Over time, this process drains NGC 7619 of the very material it needs to form new stars. With its gas removed, the galaxy becomes increasingly inert. Its young, blue stars fade, leaving only older, redder populations behind. It doesn't take long for the galaxy to transition, visually and physically, into a quiescent state. But this is more than just the loss of gas. It's an environmentally triggered metamorphosis. Without its reservoir of hot halo gas, NGC 7619 loses its ability to replenish itself. It can no longer cool that gas and condense it into molecular clouds. Star formation doesn't just decrease, it halts completely. And this process has a name in galaxy evolution models: strangulation. It's slow, silent, and terminal. The galaxy is starved to death by the environment. What makes NGC 7619 particularly valuable as a case study is that this entire transformation is visible. The galaxy is still moving fast enough to be actively stripping gas, creating a dramatic X-ray tail. That means astronomers are catching it in the act, in the very phase where the transformation from a gas-rich to a gas-poor galaxy is taking place. It's incredibly rare to observe this intermediate stage. Most galaxies are already settled, either forming stars or long dormant. But NGC 7619 is in transition, making it a priceless example for astrophysical modeling. Moreover, its morphology holds clues to its evolutionary timeline. Despite the violent motion, its elliptical shape remains intact, telling us that its stellar structure is resilient, but its interstellar medium is fragile. That distinction is crucial in understanding morphological transformation in clusters. While spiral galaxies often lose their arms and disks as they are stripped and disturbed, ellipticals like NGC 7619 can retain their form while undergoing dramatic internal change. There's also the issue of mass loss. NGC 7619 isn't just evolving in terms of gas content, it's physically shedding mass into the cluster. The stripped gas becomes part of the larger intracluster medium, enriching it with metals and altering its energy balance. This process helps seed the cluster environment with the remnants of past star formation: iron, silicon, and oxygen, all ingredients forged in supernovae within NGC 7619 long ago. In that way, NGC 7619 is not just evolving, it's contributing to the evolution of the cluster itself. And this leads to one of the most profound insights: galaxy evolution isn't just a self-contained journey. It's part of a feedback loop with the cosmos. As galaxies like NGC 7619 evolve, they change the environment around them, which in turn affects the evolution of other galaxies. The stripped gas might cool and form stars elsewhere. The added heat and metals could alter the pressure balance in the cluster. NGC 7619 is both a participant and a sculptor in the grander structure of the universe. We also begin to see why the cluster environment is sometimes described as a galaxy graveyard. Not because it instantly destroys galaxies, but because it accelerates their path towards stillness. Galaxies that fall into clusters are often transformed from active to passive. They lose their gas, slow their rotation, and fade over time. NGC 7619 exemplifies this slow march toward entropy. It is, in essence, being recycled by the universe, its raw materials stripped, repurposed, and redistributed. This makes it more than just a single story, it's a template. In galaxy evolution models and simulations, galaxies like NGC 7619 help us understand what happens to systems entering clusters. They validate predictions about gas loss, heat transfer, and morphological survival. They allow us to trace timelines. How long does it take for a galaxy to be quenched? How far into a cluster must it go before the environment overwhelms it? NGC 7619 provides answers. And perhaps most powerfully, it shows us that motion is destiny. NGC 7619 is not evolving randomly. It is evolving because it is moving, because it is falling, because it is interacting. Its speed through the cluster, its trajectory, its collisions, all of these factors shape what it is becoming. If it had remained in isolation, in the cosmic void, its story would have been entirely different. It might still possess its halo gas. It might still form stars. But fate placed it in Pegasus I, and Pegasus I is rewriting its history. When we look at NGC 7619, we are not just seeing a galaxy in motion, we are seeing galaxy evolution in motion. It is a living example of transformation, a cosmic chrysalis caught mid-metamorphosis. Its future is being sculpted by invisible forces, and we are lucky enough to watch it unfold. The transformation of NGC 7619 is not just a story of speed or violence. It is, at its core, the tale of a galaxy quietly aging, being reshaped by its environment into what astronomers sometimes poetically refer to as a cosmic retirement home. It might seem strange to think of a galaxy, an immense structure of matter, and energy spanning hundreds of thousands of light years, as retiring. But that's precisely what's happening here, slowly and inexorably, as its potential is drained away and its star-making days come to an end. NGC 7619, as we've seen, is losing its gas. The lifeblood of star formation is being stripped by the invisible storm of the intracluster medium through ram pressure and dynamic motion. Without that gas, star birth ceases entirely. And with no new stars being formed, only the old stars remain, those that have been shining for billions of years, long past their prime, inching closer to the ends of their nuclear lives. This is how a galaxy becomes a retirement home for stars. No more children are born, and the population slowly ages, growing dimmer, redder, and more inert. The first sign of this transformation is color. Galaxies like NGC 7619 that are no longer forming stars become increasingly red. Not because the galaxy is physically turning red, but because blue stars, young, massive, and short-lived, are no longer being born to replenish the population. The ones that once existed have already lived out their brief, bright lives and have died, leaving only the older, cooler, redder stars behind. This shift in population alters the integrated color of the galaxy, and to astronomers, it becomes a telltale sign of a quiescent system. Then comes the drop in luminosity. With no massive blue stars lighting up the galaxy, the overall brightness of NGC 7619 begins to fade, very slowly over cosmic timescales. Red stars like K and M types dominate, long-lived and steady, but much dimmer. Their output can't compete with the young, hot stars that once contributed heavily to the galaxy's shine. Eventually, the galaxy becomes one of the fainter members of the cluster's population, still grand in size and mass, but quietly glowing in the background of a universe that continues to evolve without it. The cessation of star formation also leads to a decline in stellar feedback. In a galaxy where stars are still forming, supernovae and stellar winds inject energy back into the interstellar medium, keeping it stirred, heated, and sometimes preventing the collapse of clouds that would otherwise condense too quickly. But in a galaxy like NGC 7619, this feedback loop ends. The last major supernovae likely occurred millions of years ago, and the absence of young stars means there's no longer a mechanism to regulate or rejuvenate the gas that remains, if any remains at all. It becomes a static environment, lacking the turbulence and energy injection that mark active galactic ecosystems. And as all of this unfolds, the stellar population evolves. The red giant phase, white dwarfs, neutron stars, and possibly even black holes begin to dominate the legacy of star formation in the galaxy. NGC 7619 becomes a silent archive of stellar evolution, a galactic nursing home where stars live out the final acts of their lives, contributing only mass and gravity to the structure as they dim and fade away. In this way, NGC 7619 is no longer a factory of creation, but a repository of history, a living memory of a more dynamic past. But this transformation is not exclusive to NGC 7619. It is the destiny of many galaxies, especially those that reside in the heart of clusters. The environmental factors that led to the stripping and quenching of NGC 7619 are part of a larger cosmic trend. When galaxies enter dense clusters, they are subjected to conditions that accelerate their aging. They lose gas to ram pressure, are heated by shocks and turbulence, may be gravitationally harassed or even merged with others, and are often permanently altered. Over time, they all tend toward passivity, a gradual decline into galactic senescence. This is one reason why the cores of galaxy clusters are often populated by so-called red and dead galaxies. These massive elliptical and lenticular systems have already undergone this transition, just like NGC 7619 is now experiencing. They serve as the final state for many galaxies, massive but no longer active, gravitationally dominant but no longer creative. They are surrounded by the X-ray glow of the intracluster medium, enriched by the very gas they once lost. It is a kind of cosmic irony. The cluster shines with the discarded material of the galaxies it has quieted. The label, retirement home, may sound poetic, but it's rooted in this very reality. Just like aging populations in human society, These galaxies house aging stars, contribute less to future generations, and become stable, quiet entities in the universe's grander evolution. They don't go away, they linger, often for tens of billions of years, but their roles shift. From creators to curators, from nurseries to mausoleums. They exist as reminders of what once was. Yet even in this apparent stillness, NGC 7619 retains importance. Galaxies in this stage contribute gravitationally to the dynamics of the cluster. Their interactions with smaller galaxies can still trigger mergers. Their cores may still harbor supermassive black holes, remnants of a more violent, active past, that can occasionally flare to life if they accrete gas. Their outer halos may continue to grow faintly through minor mergers, even as they no longer form stars internally. Moreover, their aging stars continue to evolve. White dwarfs cool over eons. Neutron stars spin down. Stellar remnants continue to shape the radiation profile of the galaxy. There is still motion, still transformation, but it occurs on long timescales, imperceptible except through the lens of deep cosmological observation. And what of the gas that was lost? It doesn't vanish. It joins the broader ecosystem of the cluster, helping maintain the high-energy plasma that fills the space between galaxies. That gas may someday be involved in star formation again, not inside NGC 7619, but perhaps in a different galaxy, or as part of an interaction that redistributes material anew. In that sense, the gas lives on, just not in its place of origin. Thus, NGC 7619 becomes part of a cosmic cycle. Born with stars and gas, it lived a productive youth, evolved through interaction, lost its vitality to external forces, and now coasts into a tranquil, quiet age. And yet, through all this, it contributes to the balance and structure of the universe. It is a monument to the processes that build galaxies, tear them apart, and recycle their components. It's not dead, it's retired, resting in a cluster whose harsh environment has ensured that its star-forming days are over, but not its role in the cosmos. In the silent halls of the Pegasus I cluster, NGC 7619 glides onward, stripped of its voice, but heavy with memory. It is the echo of cosmic time, proof that galaxies don't simply vanish when they age. They persist, massive and grave, carrying the fossil light of a past that helped build the universe we see today. As NGC 7619 continues its silent supersonic plunge through the Pegasus I cluster, its motion tells us far more than just a story about the galaxy itself. It acts like a cosmic probe, revealing hidden truths about the cluster that surrounds it. Its velocity, its shockwave, its stripped tail, they all serve as clues etched into the fabric of space, pointing toward a more complex and dynamic history of the Pegasus I cluster than might otherwise be apparent. In a way, NGC 7619 is a messenger from the past, carrying with it the signatures of ancient mergers, gravitational infall, and the slow, violent evolution of galaxy clusters over billions of years. To understand how this galaxy reveals such secrets, we must first recognize that galaxy clusters are not static collections of galaxies. They are living, growing structures, built up through the merging of smaller groups, the accretion of galaxies, and the coalescence of dark matter halos. Just like galaxies evolve, so too do clusters, though on a grander and slower scale. And much like tectonic plates shifting beneath Earth's surface reveal past earthquakes and continental drift, the motions of galaxies within a cluster unveil the cosmic tectonics at work within the cluster environment. The sheer speed of NGC 7619, over 1,400 km per second, immediately raises eyebrows. That velocity isn't random. For a galaxy to be moving that fast relative to the intracluster medium, something dramatic must have occurred in its recent history or in the environment it inhabits. It's not merely falling gently into the cluster's gravitational well, it's barreling through it. This hints at a recent or ongoing infall event, where NGC 7619 may be part of a subgroup of galaxies that is still in the process of merging with the central core of Pegasus I. Such subgroups are common in clusters. In fact, many clusters are not fully relaxed systems. They continue to grow through the infall of smaller associations of galaxies, each carrying their own stars, gas, and dark matter. If NGC 7619 originated from such a group, perhaps along with its close companion NGC 7626, then its trajectory and velocity may represent the direction and energy of that group's descent into the cluster. The shockwave detected in X-rays behind NGC 7619 is a smoking gun for this theory. It shows that the galaxy is plowing through a relatively stationary medium, suggesting that it has only recently arrived and has not yet settled into a stable orbit. Even more compelling is the alignment of NGC 7619 and NGC 7626, the two brightest galaxies in Pegasus I. Both show signs of motion, both possess X-ray tails, and both are likely at the centers of their own dark matter halos. Some astronomers suggest that what we're seeing in Pegasus I is the ongoing merger of two galactic subgroups, each centered around one of these massive ellipticals. If true, then the supersonic motion of NGC 7619 isn't just an individual anomaly. It's a direct signature of cluster-scale evolution. In this scenario, Pegasus I becomes a kind of cosmic battlefield, where two large gravitational factions are converging. The galaxies within each group carry their inherited velocities, and as they collide, the hot plasma between them resists this motion, creating the conditions for ram pressure, shock fronts, and turbulent mixing. These phenomena don't just affect one or two galaxies. They ripple through the entire structure, heating the intracluster medium and altering the trajectories of hundreds of other galaxies. NGC 7619, by leading this charge, becomes the tip of the spear, making its motion a map of the larger gravitational war unfolding in Pegasus I. Moreover, the shape and extent of NGC 7619's X-ray tail can help trace the density and temperature profile of the cluster's gas. The fact that the tail is long, coherent, and clearly defined suggests that the galaxy is moving through relatively dense, consistent plasma, likely near the cluster's core. By studying how the gas is being stripped, astronomers can infer the local pressure, temperature, and density gradients of the intracluster medium. This turns NGC 7619 into a diagnostic tool, not just for motion, but for the physical conditions of the environment it travels through. Astronomers can also use the velocity of NGC 7619 to test mass models of the cluster. The speed at which a galaxy moves through a cluster depends on the gravitational potential, which in turn is dominated not just by the visible galaxies, but by dark matter. If NGC 7619 is moving at supersonic speed, that implies the gravitational potential of Pegasus I is deep and wide enough to support such velocities without ejecting the galaxy entirely. If not, then NGC 7619 might be on a radial path, soon to escape the cluster altogether. Either way, the galaxy's motion becomes evidence for the distribution of unseen mass, and therefore for the structure and evolution of dark matter in clusters. There's also an opportunity to look further back in time. If NGC 7619 is now plunging through Pegasus I, what was its trajectory over the past few billion years? Where did it come from? Simulations suggest that galaxies often fall into clusters from surrounding filaments, the vast, thread-like structures of the cosmic web. NGC 7619 may have traveled along one of these filaments, gathering speed as it was gravitationally pulled inward. By mapping its current velocity and direction, and comparing it with the positions and motions of nearby galaxies, researchers can attempt to reconstruct the infall history of the cluster. It's a bit like watching ripples on a pond and working backward to figure out where the stone was thrown. Even more intriguingly, NGC 7619's current path might one day lead to a major merger. If it's on a collision course with another massive galaxy in Pegasus I, perhaps NGC 7626, the future holds yet more transformation. The impact could trigger shockwaves, change the shape of the galaxies, fuel the central supermassive black holes, and heat the surrounding gas further, continuing the long saga of cluster assembly. The evidence for such a future lies in NGC 7619's current motion, and careful observation of its trajectory helps astronomers predict what comes next in the evolution of Pegasus I. In all these ways, NGC 7619 is more than a lone, fast-moving elliptical. It is a living data point, a dynamic relic, a tracer of the cluster's growth, and a revealer of the invisible. Its behavior is written into the cluster's history, like a meteor burning through an atmosphere, glowing not only from its own fire, but from the friction of the environment it tears through. By studying it, we peel back the layers of Pegasus I's past. We learn when subgroups joined, how dark matter has shaped the gravitational landscape, and how galaxies are transformed by their journeys into these colossal structures. It's a kind of forensic cosmology, using motion and morphology to reconstruct the ancient and ongoing history of a galactic ecosystem. And what's most remarkable is that NGC 7619 didn't volunteer for this role. It's simply following the gravitational path laid before it, plunging ahead, shaped by forces far beyond its control. Yet in doing so, it reveals everything, from its own life story to the larger narrative of how clusters like Pegasus I came to be, and how the universe continues to build itself, one collision, one merger, one supersonic galaxy at a time. In the vast tapestry of the cosmos, NGC 7619 is not entirely alone in its supersonic journey through a galaxy cluster. There are other galaxies that have reached or exceeded the sound speed within their environments, rocketing through the hot, dense plasma that permeates galaxy clusters. However, while the existence of other supersonic galaxies is well established, few have tails as dramatic, shock fronts as defined, or motion as well documented as NGC 7619. This makes it not just part of a rare club, but a standout member, a cosmic exemplar of speed, transformation, and intergalactic violence. To put this into context, we need to look at the broader class of what astronomers call ram pressure-stripped galaxies, which are often the most likely candidates for supersonic behavior. These galaxies exhibit the telltale signs of high-velocity interactions with the intracluster medium, tails of stripped gas, bow shocks, truncated star-forming disks, and sometimes trails of new stars forming in their wake from the gas they've lost. Some of these galaxies are spirals being transformed into lenticular or elliptical systems. Others are already early-type galaxies, like NGC 7619, that are undergoing the final phase of environmental evolution. One of the most well-known examples outside of NGC 7619 is ESO 137-001, a spiral galaxy hurtling through the Norma cluster. This galaxy is notable for its spectacular multi-wavelength tail, one that glows in X-rays, optical light, and hydrogen alpha emissions. The tail stretches for over 260,000 light-years, and the galaxy is moving at a velocity similar to or even exceeding that of NGC 7619. In ESO 137-001's case, the ram pressure is triggering star formation in its tail, creating brilliant knots of young stars. It's a supersonic galaxy in every sense, but with a very different appearance and evolution due to its spiral nature. Then there's NGC 1404, a bright elliptical galaxy in the Fornax cluster. It too is moving at high velocity, possibly supersonic, through the intracluster medium, and Chandra observations have revealed a leading-edge bow shock. Like NGC 7619, NGC 1404 is an elliptical galaxy being stripped of its hot gas as it falls into the cluster's core. It has an X-ray tail, albeit shorter and more diffuse, and it has helped astronomers understand the stripping process in more massive systems. Another galaxy worth mentioning is M86 in the Virgo cluster. M86 is also moving at extraordinary speed, estimated at over 1,500 km per second, relative to the ambient intracluster medium. It trails an X-ray plume behind it, and has likely been stripped of most of its gas. What's interesting about M86 is that it may also be on a highly radial orbit, just like NGC 7619, meaning it could be plunging into the Virgo cluster for the first time. This motion gives insight into the timing and nature of galaxy infall, and M86, like NGC 7619, serves as a probe of cluster dynamics. However, even among this group of high-speed travelers, NGC 7619 still holds a special place. First, its motion has been exceptionally well documented, not just through its velocity estimates, but through the accompanying X-ray data that reveals the presence of a shock front, a literal sonic boom in space. This is a rare phenomenon. While many galaxies are stripped, few are confirmed to be moving fast enough to create a shockwave visible in the X-ray spectrum. The detection of such a shock front by Chandra is what truly elevates NGC 7619 to a different level of significance. It's not just fast, it's sonically fast in the medium through which it moves. Additionally, NGC 7619's long and coherent X-ray tail, a signature of ongoing ram pressure stripping, is one of the most dramatic among elliptical galaxies. Unlike spiral galaxies like ESO 137-001, which often show complex tails with clumps of star formation, NGC 7619's tail is smooth and diffuse, consistent with a hot gas halo being gently peeled away rather than star-forming material being violently ejected. This makes it a cleaner case for studying the effects of high-speed motion on early-type galaxies, where the physics is dominated more by pressure and less by starburst-driven winds. In terms of scientific value, NGC 7619 is also exceptional because it is a part of a binary system with NGC 7626, and both galaxies exhibit signs of high-speed motion. This provides a rare opportunity to study multiple galaxies undergoing transformations simultaneously within the same cluster. The interaction between these two galaxies and the surrounding intracluster medium allows astronomers to build models of cluster assembly, subgroup mergers, and environmental processing on multiple scales. Furthermore, most known supersonic galaxies have been observed in larger, denser clusters like Virgo, Fornax, or Coma. NGC 7619's residence in Pegasus I, a relatively less massive and lower density group compared to something like Coma, adds another layer of uniqueness. It shows that supersonic stripping isn't exclusive to the richest clusters. Even in smaller, more dispersed groups, galaxies can attain velocities and environmental conditions sufficient to undergo dramatic transformations. This helps refine our understanding of where and how galaxy evolution can be accelerated. Finally, the clarity of the observations, across X-ray, optical, and radio wavelengths, gives NGC 7619 a robustness that few other examples can claim. Some galaxies show signs of fast motion, but without corresponding X-ray confirmation. Others exhibit tails or gas loss, but lack the context of a well-mapped environment. NGC 7619 sits in a sweet spot of detectability, interpretability, and relevance. It's not just a fast-moving galaxy, it's a well-lit laboratory in the sky, offering a clear window into the physics of galaxies in motion. In a universe of trillions of galaxies, the supersonic few offer exceptional opportunities to study the invisible, to see motion without sound, pressure without touch, and transformation without collision. And among them, NGC 7619 stands tall. Not because it is alone, but because it is one of the few that allows us to witness the full drama of galactic motion laid bare in X-ray light, with every stripped particle telling us not only how it's moving, but what it's moving through, and what it's leaving behind. The reason astronomers devote so much time and effort to studying galaxies like NGC 7619 goes far beyond curiosity about a single fast-moving elliptical drifting through space. In fact, galaxies like NGC 7619 serve as crucial laboratories, windows into the grand cosmic processes that shape the structure of the universe itself. Observing this one galaxy can help us unravel the mysteries of galaxy evolution, cluster dynamics, cosmic weather, and even dark matter physics. These aren't abstract scientific terms, they represent the story of how the universe formed, changed, and continues to evolve over billions of years. At its core, the study of NGC 7619 helps answer one of astronomy's most fundamental questions: how do galaxies change over time? It's easy to assume that once galaxies form, they remain relatively stable, quietly aging while their stars burn out. But this couldn't be further from the truth. Galaxies are dynamic, evolving entities, and their transformation is driven not just by internal processes like supernovae or black holes, but also by their environment, especially when that environment is the hot, turbulent interior of a galaxy cluster. NGC 7619 is particularly important because it's a textbook example of a galaxy undergoing environmental transformation in real time. We are watching it as it gets stripped of its gas by the intracluster medium, as it leaves behind a trail of its former self glowing in X-ray wavelengths, and as it reacts to the pressure, motion, and forces surrounding it. Studying this process directly allows scientists to test theoretical models of how galaxies evolve after they enter dense environments. Without such real-world examples, those models would remain mathematical abstractions. NGC 7619 provides the evidence, tangible, visible, and measurable. One key area where this evidence is critical is in understanding cosmic weather. While space may seem like an empty vacuum, galaxy clusters are filled with hot, ionized gas known as the intracluster medium, ICM. This medium is anything but calm. It's a stormy, high-energy plasma that reacts to gravitational shifts, mergers, and galaxy motion. When a galaxy like NGC 7619 moves through this environment, especially at supersonic speeds, it experiences the full force of this invisible storm: pressure, friction, heat, turbulence. This interaction produces shockwaves, heats the gas, and shapes the galaxy's future. By studying these interactions, astronomers can understand the physics of the ICM itself, its temperature, density, pressure, and how it changes over time. This is important because the intracluster medium makes up more of the normal, visible matter in a cluster than the galaxies do. The stars we see are just a fraction of what's out there. Most of the baryonic, normal, matter exists in the form of this hot, X-ray emitting gas, and yet it's largely invisible unless you have specialized instruments like the Chandra X-ray Observatory or XMM Newton. Galaxies like NGC 7619, through their interactions, illuminate the invisible. Their stripped gas trails and bow shocks highlight where the ICM is densest or hottest, and help map the contours of the otherwise unseen cluster weather. But the implications go even further. By observing galaxies that undergo ram pressure stripping and supersonic travel, scientists can understand how star formation is quenched. Star formation is the engine of galactic youth. It determines a galaxy's color, brightness, and shape. When a galaxy is stripped of its gas, it can no longer form new stars. It grows redder, dimmer, and quieter. NGC 7619 shows us how this process unfolds in detail. From the moment it begins to lose its gas, we can track how long it takes for star formation to cease, how much mass is lost, and how that loss affects its morphology. This process helps explain one of the major observed patterns in the universe: why galaxies and clusters are different from those in the field. Isolated galaxies, those floating freely in the cosmic void, tend to be blue, active, and forming stars. Cluster galaxies are often red, passive, and elliptical. NGC 7619 is living proof of how galaxies make that transformation. Studying it helps us understand not just individual galaxies, but entire galaxy populations across cosmic time. Furthermore, NGC 7619 allows researchers to probe the gravitational architecture of its home cluster, Pegasus I. Its motion, tail, and interaction with the ICM provide data points for determining the distribution of mass, especially the elusive dark matter that dominates the gravitational potential of galaxy clusters. The speed at which NGC 7619 is moving, for instance, suggests how deep the cluster's gravitational well is, and how mass is arranged within it. That helps scientists model not only Pegasus I, but other clusters and the large-scale structure of the universe. There's also the importance of multi-wavelength astronomy. NGC 7619 is not visible in the X-ray alone, it's also been observed in optical, infrared, and radio. Each wavelength tells a different part of the story. Optical light shows the stars, X-rays show the hot gas and shockwaves, and radio can reveal the presence of magnetic fields or jets from a central black hole. This kind of comprehensive observation helps validate the tools astronomers use across the board. It connects theory to observation in a way that few galaxies can match. From a cosmological perspective, galaxies like NGC 7619 also serve as fossil records. They carry the marks of their past interactions, minor mergers, infall history, orbital paths, all encoded in their structure, motion, and gas content. By analyzing these clues, astronomers can reconstruct the assembly history of galaxy clusters, understanding when and how they grew, what smaller structures fell into them, and how their dynamics evolved. This, in turn, feeds into our knowledge of structure formation in the universe, a central piece of modern cosmology. Then there's the human side of it, the philosophical weight of watching a galaxy in transformation. NGC 7619 reminds us that change is constant, even on the scale of billions of stars. It forces us to rethink what we mean by stillness and quiet. To the naked eye, it may appear like a featureless smudge. But in truth, it's in the midst of a battle, shedding parts of itself, adapting to a hostile environment, and writing its final evolutionary chapters. It is a story of struggle, endurance, and transition. So, when astronomers focus their most powerful telescopes on a galaxy like NGC 7619, they aren't just studying one object in isolation. They're watching the universe in action, testing theories, refining models, learning the rules of cosmic survival. NGC 7619 is not just a case study in speed, it's a case study in consequence. The stripping of its gas shows how environment influences destiny. The shape of its tail reveals the structure of the cluster around it. Its motion maps the invisible dark matter landscape. Its quiet future foretells the fate of many galaxies yet to come. In that sense, NGC 7619 is both a mirror and a map. A mirror reflecting the processes that govern the life cycle of galaxies across the cosmos, and a map pointing toward the deeper, often hidden mechanics of the universe itself. It teaches us that nothing in the universe evolves alone, and that even the quietest galaxies are part of a larger, turbulent, and breathtakingly intricate story. In the seemingly tranquil darkness of space, some of the most dramatic events play out in wavelengths our eyes cannot see. The tale of NGC 7619, the supersonic giant tearing through the Pegasus I cluster, is not one that unfolds in visible light. Its shockwaves, its stripped gas tail, the very evidence of its violent transformation, all remain hidden from view unless we peer into the X-ray spectrum. This is where X-ray astronomy becomes not just useful, but indispensable, and why observing the invisible has become one of the most revolutionary developments in modern astrophysics. To understand what NGC 7619 is really going through, astronomers must look beyond the stars and dive deep into the hot, diffuse plasma that fills the galaxy cluster. This plasma, the intracluster medium, exists at temperatures of tens of millions of degrees Kelvin, far too hot to emit visible light. At these extreme temperatures, the atoms in the gas are completely ionized, stripped of their electrons, and in a constant state of high-energy collision. These energetic particles emit X-rays, making X-ray observations the only way to actually detect and map this elusive component of the universe. Without X-ray telescopes, we wouldn't even know that NGC 7619 is plowing through such an environment. The galaxy itself, seen in optical telescopes, might look like just another smooth elliptical, unchanging, unremarkable. But with instruments like NASA's Chandra X-ray Observatory, astronomers can see the full picture, the bow shock ahead of the galaxy, the long trailing tail of gas stretching behind it, the glow of compressed, heated material all around. It's like switching on a different kind of light and suddenly discovering an entire hidden world. What X-ray astronomy reveals is nothing short of stunning. In the case of NGC 7619, Chandra observations show a sharp discontinuity in X-ray brightness and temperature in front of the galaxy's motion, a bow-shaped arc, indicating a shock front. This is the signature of supersonic travel through the intracluster medium. The gas in front of the galaxy is compressed and heated as NGC 7619 forces its way through the cluster's plasma. This is the cosmic equivalent of a sonic boom, a phenomenon we know from jets on Earth but now observed in the scale of entire galaxies. Trailing behind NGC 7619 is the X-ray tail, an extended plume of stripped material. This tail doesn't just mark where the galaxy has been, it's a record of how much of its hot gas halo has been peeled away by ram pressure. The tail glows brightly in X-rays because the stripped gas is still extremely hot, heated both by the galaxy's own motion and the interactions with the surrounding medium. This stripped material tells us how quickly and how violently the galaxy is being changed. It can also help us calculate the density of the cluster gas, the speed of the galaxy, and even the gravitational forces at work in the larger environment. What makes this especially powerful is that no other wavelength reveals these details so clearly. In visible light, we see stars. In infrared, we see dust. In radio, we see cold gas or magnetic fields. But in X-rays, we see the most energetic events, the regions where physical forces reach their most extreme. It is only in X-ray that we can map the heat, trace the pressure, and visualize the shockwaves of galaxies moving through a cluster. Without this ability, much of what NGC 7619 is experiencing would remain entirely hidden. Moreover, these observations are not just about NGC 7619, they offer insights into the broader mechanics of cluster environments. For example, by analyzing the shape and temperature gradient of the shock front ahead of the galaxy, astronomers can determine the Mach number of its motion, how many times faster than the local sound speed it's moving. This helps refine models of ram pressure stripping, shock heating, and gas dynamics in clusters. It also allows comparisons with other galaxies undergoing similar processes in different environments, enriching our understanding of galaxy evolution across the universe. There's also a profound diagnostic advantage to X-ray imaging. Because the intracluster medium is so sensitive to disturbances, even small shifts, like the motion of a galaxy group or the presence of substructure, can create ripples or asymmetries that only X-rays reveal. In the case of NGC 7619, the orientation of its X-ray tail, the curvature of its shock front, and the surrounding temperature distribution all hint at larger cluster dynamics, including possible ongoing mergers or infall events. And then there's the precision. With Chandra's subarc-second resolution, astronomers can pinpoint the exact location of density discontinuities, temperature gradients, and gas mixing layers in and around galaxies like NGC 7619. This is more than just photography, it's plasma physics on a cosmic scale, and it requires the kind of data that only X-ray astronomy can provide. Yet these observations are not easy. Detecting X-rays from distant galaxies like NGC 7619 requires extremely sensitive detectors and long exposure times. The signals are faint, the backgrounds complex, and the calibration demanding. But the payoff is enormous. Each image captured by Chandra or XMM Newton adds a piece to the puzzle, not just of one galaxy's journey, but of the forces shaping the entire cosmos. What's also compelling is that X-ray astronomy often reveals features before they are seen in any other wavelength. For instance, the tail of stripped gas from NGC 7619 may not glow in optical or infrared light for millions of years, if ever, unless star formation somehow occurs in the debris. But in X-rays, that gas is already visible, already telling its story. This allows scientists to study events in their early stages, catching the action as it unfolds rather than relying on fossil records left behind in older, more evolved systems. And in the grandest sense, observing these invisible structures helps us see the true shape of the universe. While stars define the beauty of the night sky, it is the plasma, the hot gas, and the dark matter, often visible only through their interactions with this gas, that truly structure the cosmos. Without X-ray astronomy, we would be blind to half the story, unaware of the weather systems raging within clusters, oblivious to the pressure and violence that sculpt galaxies like NGC 7619 into what they eventually become. So, when we point X-ray telescopes at the sky, we're not just chasing exotic images. We're observing the hidden machinery of the universe. We're detecting the invisible winds that blow between galaxies, the invisible waves that ripple through clusters, the invisible transformations that mark the lives and deaths of galaxies. And through all of this, we find stories like that of NGC 7619, silent, supersonic, and spectacular, not in what we can see, but in what we've only just learned to perceive. It's easy to imagine galaxies as timeless titans, majestic, serene, and far removed from the chaos we associate with violence. From a distance, NGC 7619 might appear just so, a luminous elliptical shape suspended in the void, a quiet relic of an ancient universe, slowly drifting among the stars. But this is an illusion born of scale and distance. In truth, NGC 7619 is not gliding peacefully through space, it is enduring a relentless cosmic siege. Beneath its calm exterior, it is fighting a battle against forces far beyond anything we might consider peaceful. And unlike wars waged on planets, this one has no smoke or fire, just pressure, heat, gravity, and time. This galaxy, a magnificent elliptical of vast proportions, is not static. It is moving, hurtling, at over 1,400 kilometers per second through the Pegasus I cluster. And in doing so, it is facing a storm more punishing than any hurricane or supersonic wind that we could ever experience. The very fabric of the environment it travels through, the hot, ionized gas of the intracluster medium, acts like a ceaseless, invisible wind, pushing back against it with crushing force. And as it speeds along, NGC 7619 is being stripped, shredded, and reshaped by this invisible enemy. Imagine the surface of a spacecraft exposed to the friction and fury of atmospheric re-entry, only scaled up to galactic proportions, and lasting not for minutes, but for hundreds of millions of years. That's what NGC 7619 is enduring. A galactic storm rages around it, but the violence is invisible to human eyes. It manifests in X-ray light, as hot plasma glows with the friction of motion and compression. It manifests in the trailing tail of stripped gas, extending behind the galaxy like the tattered cloak of a weary traveler. And it manifests in the bow-shaped shockwave ahead of the galaxy, a sign that it is pushing against the cosmic wind so fast, it has breached the sound barrier of the very medium that surrounds it. This is what it means for a galaxy to be under siege. Not by enemies with weapons or armies, but by the sheer hostility of its environment. NGC 7619 is being robbed of the very material it needs to sustain its future. The gas that once nourished stars and fueled the slow churn of galactic evolution is being blown away, stripped out of its gravitational grasp. Every kilometer it travels forward is a kilometer of loss. And unlike the bright fireworks of a supernova or the chaotic spiral of a galactic collision, this violence is cold, continuous, and mercilessly efficient. But NGC 7619 is not defenseless. It is a product of ancient time, its stars are old, its core stable, its mass immense. Though the gas is being torn from its outer halo, the stellar population remains intact. The heart of the galaxy endures, even as the winds try to tear away its edges. This resilience is part of what makes elliptical galaxies like NGC 7619 fascinating. They are the survivors of 1,000 past battles, galactic mergers, gravitational encounters, internal explosions, and now they face their final challenge, the slow death of suffocation in a cluster's hot breath. This stage in a galaxy's life, when it enters a cluster and begins to lose its gas, is one of its final great transformations. NGC 7619 has likely lived for billions of years. It has merged with companions, swallowed smaller galaxies, and built up its massive structure. But now it finds itself in a new environment, one where the rules have changed. Here, survival isn't about growing larger. It's about holding on. Holding on to gas, holding on to shape, holding on to identity. This is not just evolution, it is attrition. The Pegasus I cluster does not welcome newcomers gently. It bathes them in high-energy plasma, buffets them with pressure, and strips them down. NGC 7619's position at the heart of this storm makes it both a victim and a beacon. Astronomers look at it not just because it is unique, but because it tells us so much. It is a galaxy that wears its trauma openly, the X-ray tail a wound, the shockwave a scar, the dwindling gas reserves a record of what it's lost. These signs aren't just important for understanding this one galaxy, they're essential for understanding all galaxies that fall into clusters. NGC 7619 is the test case, the proof that cluster environments are not benign but fundamentally transformative. Its current suffering is not without consequence. The stripping of gas means that new stars will no longer be born in NGC 7619. It is transitioning from a place of activity to a place of silence. Over time, its already aged stars will continue to cool and die. no new generations will take their place. The galaxy will redden, dim, and become more diffuse. The stripping, once complete, will leave it as a cosmic fossil, a relic of what it once was, quietly orbiting within the cluster's gravitational hold, a ghost among brighter, younger systems. Yet there is also something beautiful in this decay. A kind of quiet majesty in its endurance. NGC 7619 does not fight back in any active way. It does not roar or explode. It simply persists, gliding forward at supersonic speed, suffering transformation with dignity. Its path through the Pegasus I cluster is both a retreat and a triumph. It may be losing mass, but in doing so, it is helping illuminate the hidden forces of the universe. It is sacrificing its gas to reveal the properties of the cluster. It is becoming a tool for discovery. This reframing turns the galaxy from a passive object into an active participant in cosmic evolution. It is not merely being acted upon, it is bearing witness, and in the process, it is becoming a storyteller. Every photon of X-ray light that Chandra detects from its tail is a message. This is what happens here. This is how galaxies die. This is how clusters evolve. And though it may be silent to us, unable to voice its torment in sound, the physics speaks volumes. The supersonic shock, the stripping tail, the changing stellar population, these are its language. They tell us of a galaxy that, far from being static and ancient, is alive with change, engraved with motion, and etched by the environment in which it now finds itself. It is this duality that makes NGC 7619 so profound. It is both majestic and vulnerable, ancient and active, still and yet moving at breakneck speed. It shows us that even the largest and oldest structures in the universe are not immune to transformation. That even the serene can be storm-tossed. That even the mighty can be worn down, reshaped, and reborn into something new. To gaze upon NGC 7619 is to see the majesty of a galaxy under siege, one that does not collapse, but adapts, one that does not scream, but shines. A silent warrior enduring the eternal winds of the cosmos. In the stillness of space, there is no atmosphere to carry a scream, no air to ripple with a sonic boom. It is a vacuum, profoundly silent, utterly mute. And yet, despite this silence, NGC 7619 has done something extraordinary. Something that we associate with the roaring thunder of jet planes, the sharp crack of a whip, or the shockwave of an explosion. This galaxy has broken a sound barrier. Not in the way we perceive with our ears, but in a deeper, more fundamental physical sense. NGC 7619 is moving faster than sound travels through the medium it occupies. In the realm of astrophysics, this is what makes it a supersonic galaxy. It might seem counterintuitive. After all, isn't space supposed to be empty? What does it even mean for something to move faster than sound? In a vacuum? The key lies in understanding that space, at least in galaxy clusters, is far from empty. The Pegasus I cluster, like other galaxy clusters, is suffused with a hot, thin gas called the intracluster medium, ICM. This plasma, composed mostly of ionized hydrogen and helium, is spread out across millions of light years, and though its density is incredibly low compared to Earth's atmosphere, it still behaves like a fluid in many ways. Because this medium has mass, temperature, and pressure, sound can travel through it, albeit in a very different form than the sound we experience on Earth. In this context, sound is not an audible wave but a compression wave, a propagation of pressure changes through the hot plasma. The speed of this wave, the speed of sound in the intracluster medium, depends on the temperature and composition of the gas. In the Pegasus I cluster, where temperatures soar into the tens of millions of degrees Kelvin, the sound speed is estimated to be around 1,000 to 1,300 kilometers per second. Now consider NGC 7619. Based on careful measurements of its motion through the cluster, derived from redshift analysis, X-ray shock front modeling, and gas dynamics, astronomers have estimated its velocity at approximately 1,400 kilometers per second. That places it above the local sound speed in the ICM. This isn't just fast, it's supersonic. And when an object moves supersonically through a fluid, No matter how tenuous that fluid may be, it creates a shockwave, a sudden, violent compression of material that forms ahead of the moving body. This is exactly what's been observed in NGC 7619. The Chandra X-ray Observatory detected a distinct edge in brightness and temperature in front of the galaxy, a bow-shaped discontinuity in the X-ray emission that maps almost perfectly to the type of shockwave one would expect from supersonic motion. This arc is not just a visual feature. It is a physical boundary where gas is being violently compressed and heated as the galaxy plows through the cluster's plasma. This is the galaxy's version of a sonic boom. It's worth pausing here to appreciate the scale and subtlety of what's happening. On Earth, when a plane breaks the sound barrier, the resulting shockwave is deafening and immediate. In the vacuum of space, there is no sound to hear, but the energy is still very real. The shockwave in front of NGC 7619 heats the intracluster medium to even higher temperatures. It alters the pressure balance in the surrounding region. It creates turbulence and wakes that affect nearby galaxies, and it can even trigger mixing of materials, stirring together different layers of gas in a dynamic, turbulent ballet. And it's not just that NGC 7619 is fast, it's what that speed means. To move supersonically through a galaxy cluster, a galaxy must either be on its first infall into the cluster, still retaining the momentum from its cosmic journey through less dense space, or it must have experienced a gravitational slingshot from interactions with other massive galaxies or subclusters. In either case, the fact that NGC 7619 is moving this fast tells us that it is a recent arrival, or that it is part of a violent dynamical event within the Pegasus I cluster. In other words, this galaxy isn't just moving, it's revealing history. The speed also speaks to its mass and momentum. NGC 7619 is not a lightweight, it's a giant elliptical, packed with stars and dark matter. To accelerate something so massive to such velocities requires immense gravitational forces. Its speed is a clue to cluster assembly, dark matter interactions, and the broader cosmological structure of its environment. By studying its motion and the shockwave it generates, astronomers can learn about the distribution of mass in the cluster, the velocity dispersion of galaxies, and the temperature structure of the surrounding gas. Furthermore, the shock front created by NGC 7619 is more than just a side effect, it is a scientific tool. By analyzing the shape and temperature gradient of the shock, researchers can determine the Mach number of the galaxy's motion, the ratio of its speed to the local sound speed. This gives precise estimates of the velocity, and allows comparison with simulations of ram pressure stripping and galaxy dynamics. It's as if NGC 7619 is a cosmic wind tunnel experiment, revealing the fundamental physics of fluid motion on intergalactic scales. This intersection of motion, heat, and structure is one of the most compelling examples of how classical physics still rules the cosmos. Concepts like the speed of sound, shockwaves, and supersonic travel, familiar from aerodynamics and high-speed aircraft, are just as valid and powerful when applied to galaxies flying through plasma at millions of kilometers per hour. The universe, in its vastness, still obeys the rules of pressure and momentum. And NGC 7619, in all its grandeur, is breaking the cosmic sound barrier not with noise, but with motion, light, and energy. But perhaps the most poetic truth of all is this: even in silence, speed leaves a mark. NGC 7619 will never create a sound we can hear. It will never announce its passage with thunder or scream. And yet, it moves so fast, it shocks the space around it. It leaves behind a signature, a glowing arc, a stripped tail, a transformed wake, that tells the story of its journey louder than any explosion. It is a silent boom, echoing not in sound, but in structure, in temperature, in the X-ray glow of its trail. In breaking the sound barrier of its environment, NGC 7619 reminds us that motion is never silent to the universe itself. The medium listens, reacts, and remembers. The plasma records every push, every shock, every ripple. And as long as we have the eyes to see an X-ray and the mind to interpret what we observe, galaxies like NGC 7619 will continue to whisper their stories across the darkness, not in words, not in sound, but in the language of physics. When we narrow our focus to a single galaxy, NGC 7619, it's easy to become captivated by its individual story, its speed, its struggle, its slow unraveling. But to truly appreciate the magnitude of what's unfolding, we must step back. We must zoom out and see the bigger picture. Because this isn't just about one galaxy racing through space, it's about a lone traveler plunging headfirst into a vast, hostile environment far beyond anything we can imagine, a galaxy cluster. NGC 7619, as massive and ancient as it is just one member of a larger collective, the Pegasus I cluster. This cluster isn't just a loose group of galaxies held together by coincidence. It's a colossal gravitational structure, one of the most massive environments in the universe. With dozens or even hundreds of galaxies, an enormous halo of dark matter, and a thick soup of hot plasma, a galaxy cluster like Pegasus I is the cosmic equivalent of an ocean, and NGC 7619 is a single, defiant ship pushing against the current. Let's first consider the scale. NGC 7619 is a giant elliptical galaxy, roughly 120,000 light-years across, larger than our own Milky Way. It contains hundreds of billions of stars, an enormous central black hole, and a halo of gas and dark matter that stretches far beyond its visible edge. But Pegasus I, the cluster it moves through, is millions of light-years wide. It contains trillions of solar masses worth of material. It has a core where gravitational forces peak, and a massive volume filled with seething, high-temperature gas. NGC 7619 is just one actor on this enormous cosmic stage, and yet its presence still makes ripples in the curtain of gas that surrounds it. And that gas, the intracluster medium, is no passive backdrop. It's a dynamic, high-energy plasma that exerts enormous pressure on any object moving through it. In this context, NGC 7619 is like a meteor blazing through Earth's upper atmosphere, but on a scale that defies imagination. The galaxy is being buffeted, stripped, and slowed by the pressure of this medium, even as gravity tries to drag it deeper into the cluster's core. The hydrodynamic forces acting on it are immense. As it moves forward, it loses its outer gas layers, forming a long tail behind it, a kind of celestial wake in the intergalactic sea. But Pegasus I is not just a gaseous battleground. It's a gravitational monster. The gravitational potential well of the cluster is deep and wide, shaped not just by the galaxies and hot gas but by an enormous cloud of invisible dark matter. Dark matter accounts for roughly 80 to 85% of the mass in a galaxy cluster. It doesn't emit light, but its gravitational pull is what keeps the cluster bound together, and what accelerates galaxies like NGC 7619 to supersonic speeds as they fall inward. As NGC 7619 races through the cluster, it's not moving in isolation. It's being acted upon by gravitational tides, drag forces, and orbital dynamics influenced by every massive object nearby. It may be orbiting the cluster's center, plunging toward it for the first time, or passing near other massive galaxies whose gravity tugs at it unpredictably. Its path is dictated not by free will, but by the invisible architecture of the cosmos, the gravitational scaffolding built by dark matter, gas, and time. And in this battlefield, NGC 7619 doesn't have a protective shield. Unlike stars or planets with magnetic fields or atmospheres, galaxies are exposed. Their gas halos are loosely bound and easily torn away. Their stars, though tightly packed in the core, can be nudged by tidal forces. Their dark matter halos, while robust, can be distorted and reshaped by encounters. And so the cluster wins, slowly and surely. It strips the galaxy bare, heating and dispersing its gas, softening its edges, and eventually silencing its ability to form new stars. The cluster reshapes the galaxy, and the galaxy reshapes the cluster in return, if only slightly. Zooming out even further, we see this struggle as a microcosm of cosmic structure formation. Galaxy clusters are not static, they're dynamic, growing entities. They build up by accreting galaxies in groups, drawing them in through gravity, stripping them of their material, and folding them into the cluster ecosystem. Every infalling galaxy like NGC 7619 adds to the cluster's mass, its complexity, its story. In fact, much of what we know about how clusters form and evolve comes from observing galaxies in various stages of this infall. So while NGC 7619 seems like the victim here, a single galaxy under siege, it's also a collaborator in a much larger evolutionary drama. Its stripped gas doesn't disappear. It enriches the intracluster medium with heavy elements like iron, oxygen, and silicon. These elements were forged in stars over billions of years and are now being recycled into the cluster's plasma, where they will remain for eons. In this way, NGC 7619 is feeding the cluster, contributing to its long-term growth, not just as a passenger, but as a participant in cosmic alchemy. This interaction is also reciprocal. The cluster, in stripping the galaxy, is enforcing a kind of cosmic conformity. Over time, galaxies and clusters tend to look alike: red, dead, elliptical. This is not a coincidence. It's the end result of countless battles like the one NGC 7619 is fighting now. By observing this galaxy, we are catching the process mid-act, seeing the transformation as it happens. And that's what makes it so scientifically and symbolically powerful. From the grandest view, the narrative becomes clear. Galaxy clusters are the final destinations of galactic evolution. They are the cosmic cities, drawing in galaxies from the suburbs of space, assimilating them into a larger whole. And galaxies like NGC 7619? They are the migrants, the travelers, the war-weary veterans crossing the void to find their place in the structure of the universe. This journey is neither peaceful nor swift. It is a slow, grinding process marked by loss, change, and eventual equilibrium. The cluster does not destroy the galaxy, but it changes it irrevocably. It pulls away its gas, silences its star birth, molds it into the quiet, red structure we associate with elliptical galaxies. The galaxy is no longer what it was, but it survives, adapts, and endures. In this epic confrontation, galaxy versus cluster, there is no clear winner or loser. There is only transformation. The cluster grows stronger, the galaxy grows quieter, and the universe continues its dance of creation and change. NGC 7619, in all its motion and suffering, reminds us that the most massive structures in the universe are not static. They are alive with motion, rich with interactions, and shaped by the forces that bind galaxies together in this grand cosmic web. As NGC 7619 continues its silent plunge through the Pegasus I cluster, we're left with a compelling and inevitable question: what lies ahead? What is the ultimate fate of this massive, ancient galaxy that is being slowly and methodically reshaped by the environment around it? Will it continue its furious motion indefinitely? Will it lose more of itself to the cluster's vast gaseous ocean? Or will it meet some even more dramatic end, like merging with another giant or dissolving into the cluster's diffuse light? The answers lie not in certainty, but in extrapolation, guided by the physics of galaxy evolution and the lessons we've learned from other cluster-bound galaxies that have already run this gauntlet. The most immediate expectation for NGC 7619's future is continued stripping. Its current trajectory through the hot, dense intracluster medium guarantees that it will continue to lose gas. The bow's shock and trailing tail already observed in X-ray light are not just temporary phenomena. They're part of a long-term process that will persist as long as the galaxy remains immersed in the high-pressure plasma of the cluster. Ram pressure stripping is efficient, especially for gas loosely bound in the outer halo. And even though much of the inner gas may remain for now, it's only a matter of time before even the deeper reserves begin to erode. The loss of this gas will have profound consequences. Without fresh fuel for star formation, the stellar population of NGC 7619 will age without renewal. It will become redder, dimmer, and more diffuse. No new stars will ignite to replace the aging, dying ones. Over hundreds of millions to billions of years, it will become increasingly quiescent, more like a fossil of what it once was. This is not a fate unique to NGC 7619. It is the expected endgame for many galaxies that enter the harsh environments of clusters. But what makes NGC 7619 special is that we're catching it in the act, witnessing it mid-transformation, with the process laid bare in glowing X-ray trails. Eventually, as it continues to orbit within Pegasus I, NGC 7619 will likely settle into a gravitational equilibrium. Its speed, though currently supersonic, will be affected by dynamical friction, a subtle but important braking effect. As it plows through the dark matter and gas of the cluster, it leaves behind a gravitational wake. This wake exerts a counterforce, gradually slowing the galaxy's motion over immense timescales. This means that NGC 7619 will not remain on its current path forever. Instead, it will likely spiral inward, sinking deeper into the cluster's potential well. This inward motion increases the chances of gravitational encounters with other galaxies. Galaxy clusters are bustling environments. Though the average distance between galaxies remains vast compared to their size, over time, close encounters become statistically likely. These encounters may be minor, resulting in gravitational nudges or stripping of stars at the outskirts, or they may be more cataclysmic, leading to mergers. A merger with another galaxy, especially another large elliptical or a smaller satellite, could dramatically alter NGC 7619's structure. It could reinvigorate its core with new material, potentially reigniting some limited star formation if any gas is introduced. Or it could lead to the growth of its central black hole, feeding it with fresh matter and possibly triggering a new phase of active galactic nucleus (AGN) activity. However, in cluster environments, dry mergers without gas, are more common, meaning the resulting galaxy would still be gas-poor and evolve into an even more massive, more spheroidal structure, devoid of star formation but rich in mass and age. In the far future, NGC 7619 may become one of the dominant central galaxies of the Pegasus I cluster, a behemoth galaxy that has merged with several of its neighbors, grown to several times its current size, and now resides in the quiet heart of the cluster, surrounded by an extended halo of stars and dark matter. Many of the largest galaxies in clusters, so-called CD galaxies, have formed in exactly this way, through repeated cannibalization of smaller galaxies over billions of years. There is also the possibility that NGC 7619's motion and gas loss will help contribute to a broader process of transformation in the cluster itself. Its stripped gas will enrich the ICM with metals, elements heavier than helium, produced in ancient stars. These metals don't disappear. They mix into the cluster's plasma and alter its composition over time, affecting cooling rates, X-ray luminosity, and future thermodynamics of the cluster's central regions. In this way, NGC 7619's fate is not just about its own transformation, it's about how it shapes the future of the cluster it now calls home. What about star formation? For NGC 7619, the chance of reviving star birth seems slim. The necessary gas is being removed, not replenished. And unlike spiral galaxies that can acquire fresh material from intergalactic filaments or companions, ellipticals and clusters rarely get a second chance. The combination of high-speed motion, low gas content, and a hostile surrounding medium means that NGC 7619 is likely moving toward complete passivity, a state where all its future changes are morphological and dynamical, rather than luminous. Still, there may be surprises. Some compact groups of galaxies within clusters manage to retain enough gas to experience delayed or rejuvenated star formation during mergers. If NGC 7619 happens to interact with a gas-rich dwarf galaxy or a stripped clump of interstellar matter, it could trigger localized bursts of activity, brief flickers of new life in an otherwise aging system. But these events would be the exception, not the rule, mere echoes of a far more active past. The long-term cosmic timeline suggests that as billions of years pass, and the universe continues to expand and cool, clusters like Pegasus I will become even more isolated. The cosmic web will stretch, filaments will thin, and galaxies within clusters will be increasingly cut off from the rest of the universe. NGC 7619, by that point, may be part of a massive central elliptical, a final monument to the golden age of galaxy formation. It may no longer resemble the dynamic, supersonic body we observe today, but instead stand as a silent colossus, surrounded by faint stars and remnants of past interactions. In the endgame of the universe, when star formation has ceased, when gas is rare, and when galaxies have settled into their final orbits, NGC 7619's journey will serve as one chapter in the great story of galactic evolution through environmental transformation. It began as a galaxy born in a quieter part of the cosmos, built through mergers and growth, traveled across intergalactic space, entered a cluster, and there met a new kind of challenge, one not of destruction, but of pressure, attrition, and change. And what lies ahead for NGC 7619 is not an explosion or an ending, but a gradual fading, a transition into a more stable, quieter existence, where it becomes not just a galaxy among many, but a memory of motion, preserved in the gas it left behind and the stars it no longer forms. At first glance, NGC 7619 appears calm. It rests in the sky with a pale, golden glow, its rounded elliptical shape exuding an air of permanence and silence. There are no spiraling arms, no bright blue clusters of young stars, no great plumes of gas bursting with activity. It looks peaceful, inert, like a cosmic monument to stillness. But this is the great deception of deep space, that what looks quiet is often not, that beneath the elegance lies struggle, and that behind every shape lies a story. NGC 7619 is the perfect embodiment of this contradiction. In its form, it is majestic, graceful in its smooth, rounded symmetry, dignified in its aged starlight. But behind that calm facade is a story of motion, violence, and transformation. The galaxy is not floating serenely in the darkness, it is plowing, supersonically, through the heart of the Pegasus I cluster. It is being bombarded, stripped, squeezed, and reshaped by forces invisible to the human eye. And that silent, golden glow? It is the light of ancient stars shining through the aftermath of a celestial battle still underway. The majesty of NGC 7619 lies not just in what it is, but in what it has endured, and what it continues to endure with quiet defiance. Unlike the brilliant chaos of a supernova or the swirling energy of a star-forming nebula, NGC 7619's drama is slower, colder, and more subtle. It is the kind of violence that doesn't shout, it whispers. It peels away its victim's breath over millions of years. And yet that whisper is etched in X-rays carved in the tail of stripped gas, and glowing in the heat of a bow shock that speaks louder than any explosion. This paradox, the marriage of mystery and majesty, is what makes NGC 7619 so captivating. To a casual observer, it might look like nothing more than a faded dot in the sky. But to those who peer deeper, who look in X-ray wavelengths and measure its motion across the cluster, NGC 7619 is a revelation. It's a demonstration of how stillness and fury can exist in the same object, how the universe doesn't need sound to scream, and how the oldest structures still tell the most urgent stories. There is mystery in its origins. How exactly did it attain its incredible speed? Was it slingshot by a gravitational interaction with another cluster member? Is it falling into Pegasus I for the first time from the outer reaches of space? Or was it part of a galactic merger event that hurled it into its current path? These questions may never have a definitive answer, but in asking them, we learn more about the invisible scaffolding that shapes the cosmos: gravity, dark matter, momentum. And then there's the majesty of its endurance. Despite being pounded by the high-energy winds of the intracluster medium, despite being stripped of the gas that fuels life, NGC 7619 remains intact. Its stellar core persists. Its ancient stars continue to orbit, shining softly as they have for billions of years. It does not fragment. It does not collapse. It moves forward, sacrificing only what it can afford to lose. This kind of resilience is not just remarkable, it's beautiful. It turns the galaxy into a symbol of cosmic dignity, weathering a storm that never ends, and doing so without ever making a sound. That silent endurance makes NGC 7619 a profoundly moving object, one that stirs both scientific wonder and poetic reflection. We are watching a galaxy age in real time, watching it enter the final phase of a long, luminous life. It is, in some ways, a dying entity, not in the sense of annihilation, but in the sense of transformation into stillness. It has run the race of star formation. It has danced through the dynamics of mergers. And now it slides into a future of quiet, passive evolution, shedding the last vestiges of its youth as it merges into the ambient fabric of the cluster. But even in that fate, there is mystery. Because even the stripped gas does not vanish. It lingers in the hot medium, glowing with X-rays, rich in metals, altering the cluster's chemistry. NGC 7619's contribution outlives the galaxy itself. It changes the environment, informs future science, and becomes part of the larger symphony of cosmic evolution. It is a participant in a story far bigger than itself. This is the real beauty of galaxies like NGC 7619. Their value isn't measured only in the stars they contain, or the brightness they emit. It's in the drama hidden beneath their surface, in the secrets they carry through space, and in the silent lessons they teach us about resistance, motion, and change. They show us that even in a universe ruled by cold physics, there is room for stories of quiet grandeur, tales of giants that travel alone, unseen in their struggle, yet never insignificant. So the next time one sees a dim smudge of light in a telescope or a faint ellipse in an astronomical image, consider what may lie behind that stillness. Consider the forces that have shaped it, the scars it hides, the motion that betrays its survival. In the case of NGC 7619, that faint light is the glowing testament to a violent, majestic journey, a galaxy that has broken the sound barrier of space not with a roar, but with relentless, unstoppable movement. It is, perhaps, the purest example of how the most profound mysteries in the universe are not always loud or flashy. Sometimes, they glide silently through the cosmos, cloaked in starlight, trailing shockwaves and secrets in their wake. NGC 7619 will never make a sound. There are no ears in space to hear, no air to carry the echo of its passing, no resonance chamber to hold its voice. Yet if galaxies could speak, if their journeys carved sound into the vacuum, then NGC 7619 would not whisper. It would thunder. Its motion, its violence, its quiet endurance, it all adds up to something unspeakably loud in the language of the cosmos. It is a symphony of forces, invisible but overwhelming, gravity pulling, plasma pressing, mass colliding with momentum. It streaks through the Pegasus I cluster like a cosmic blade, slicing the hot intracluster medium, compressing it, heating it, stirring it into turbulence. Behind it trails a ghostly plume, a luminous scar etched in X-rays, a trail of loss and persistence. It's the echo of a battle between a single galaxy and the monstrous body of the cluster itself. But unlike the shockwaves we know, those created by jets, rockets, or ruptures, this shockwave is silent. It compresses atoms without a sound. It generates heat without a roar. It glows in energy we can see, but never hear. Still, the laws of physics assure us that it is a real shock, a real boom, an astronomical Mach cone forming at the forefront of its motion. NGC 7619 has, quite literally, broken the sound barrier of its environment. Not in metaphor. In fact. And so we return to the paradox. A galaxy that looks still is actually flying. A system that seems dead is shedding its skin. A structure that glows softly in visible light is surrounded by violent arcs of compressed gas, glowing hot in X-rays, roaring with energy. And yet, through it all, silence reigns. But if we had ears large enough, tuned not to frequencies of pressure waves, but to the rhythms of gravity and heat, we might hear something else. The slow hiss of gas peeling away. The crackling tension of a bow shock pressing through plasma. The soft sigh of a galaxy giving up its future stars. Perhaps, in some impossible future, if we could listen across dimensions, we might perceive the long, fading tremor of NGC 7619's voyage. A cosmic chord struck once, resonating through time. We know this. Its legacy will ripple forever. The metal stripped from its gas will enrich the cluster's hot atmosphere for billions of years. The stars born long ago in calmer times will live on in elliptical orbits, cold and quiet, as silent witnesses to the journey. The energy released in its wake will feed turbulence into the Pegasus I cluster, stirring eddies in plasma that will outlast the galaxy itself. Its story will be written in the chemistry of surrounding space, in the light of background galaxies distorted by gravitational lensing, and in the subtle gravitational wobble of the cluster's mass. There is a kind of nobility to it all, a kind of cosmic stoicism. NGC 7619 is not just surviving the storm. It is redefining what it means to move through adversity, to change with dignity, to let go of what cannot be kept, and to carry on in silence. If it could make a sound, what would it be? Perhaps not a roar. Not a scream. Not even a whisper. Maybe it would be a single, low, vibrating tone, deep and ancient, resonating through space like a bell struck once in a cathedral made of stars. A tone that says, "I was here. I moved. I endured." And maybe that tone would never fade. Maybe, if NGC 7619 made a sound, the universe would still be ringing. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.